Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're drifting towards something enormous, invisible, and strangely comforting. A boundary so large that it surrounds every planet you've ever known, every comet you've ever heard of, every spacecraft humanity has ever launched, and even the quiet little world where you happen to be listening to this right now. Far beyond Earth, beyond Mars, beyond the icy worlds drifting in the dark outskirts of our solar system, there is a kind of wall. Not a solid wall made of stone or metal or anything you could touch with your hand, but a vast invisible border created by the sun itself, a moving shoreline in space, a protective bubble inflated by light, particles and magnetic fields. And somewhere out there, at unimaginable distances, that bubble begins to end. It is one of the strangest things about our place in the universe. We often imagine the solar system as a collection of planets orbiting peacefully around the sun, neatly arranged like ornaments on invisible tracks. But the truth is much messier and much larger. The solar system is not just planets. It is giant moving territory carved into interstellar space by the constant outward breath of our star. And tonight, we're going to travel toward the edge of it. Before we begin though, I'd love to know something. Where in the world are you listening from tonight? Is it late evening where you are? Early morning? Maybe you're curled beneath blankets while rain taps softly against the window. Maybe you're listening during a long drive, or while trying to quiet a restless mind before sleep. Wherever you are, and whenever you are, it's comforting to think that all of us are floating together inside this enormous invisible bubble around the sun. If you find this voyage relaxing, intriguing, or simply a gentle escape from the noise of the day, I'd be ever so grateful if you liked the video and subscribed. It helps this sleepy little corner of science drift out to more curious minds wandering through the dark. Now then, settle in carefully. Let your breathing slow a little. There's no rush tonight. The edge of the solar system is very far away, and fortunately for us, space is patient. For most of human history, nobody knew this wall existed. Ancient people looked upward and saw stars scattered across the night sky, but they had no reason to suspect that our sun was doing something extraordinary out there in the darkness. To them, space was mostly empty, silent, still. A giant stage sprinkled with lights. Even after telescopes arrived and we began discovering planets, moons, asteroids, and distant galaxies, the idea of a solar boundary remained hidden. The solar system seemed less like a bubble and more like a collection of objects fading gradually into space. There was no obvious edge, no fence, no cosmic warning sign reading, "You are now leaving the sun's territory." But space, as it turns out, is not empty at all. That realization came slowly. During the 20th century, scientists began discovering that the sun constantly releases streams of charged particles into space, tiny fragments of atoms, electrons and protons moving at astonishing speeds. This flow became known as the solar wind, though wind may undersell it slightly. Earthly wind might scatter leaves across your yard or ruin a carefully arranged hairstyle. The solar wind can reshape magnetic fields across billions of kilometers. Every second, the sun launches roughly 1 million tons of material outward in all directions, not occasionally, constantly. Right now, as you listen, the sun is throwing particles into space like a cosmic lawn sprinkler with absolutely no regard for utility bills. And those particles do not simply stop near Earth. They stream outward past Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and far beyond. The sun is continuously inflating a gigantic bubble in space, pushing against the thin gas and radiation drifting between stars. That bubble has a name, the heliosphere. And the wall surrounding our solar system is really the outer boundary of that heliosphere. Already, the scale becomes difficult to picture. We humans evolved to understand forests, oceans, hills, and distances measured by footsteps. Even modern cities stretch our intuition sometimes. Yet the heliosphere is so enormous that sunlight itself, travelling at the fastest speed possible in the universe, takes many hours just to reach the planets, and many more to approach the outer regions of this solar bubble. To reach the boundary itself, you would need to travel for years at the speed of light. And still, despite its size, this invisible structure moves through the galaxy alongside us. That part feels strangely easy to forget. The solar system is not sitting still. The Sun is orbiting the centre of the Milky Way at roughly 828,000 kilometers per hour. Earth is orbiting the Sun. The Moon is orbiting Earth. Everything is moving all the time in overlapping patterns so complicated they almost sound invented. Meanwhile, the heliosphere travels with us like the bow wave around a ship crossing a dark cosmic ocean. And outside it, beyond the boundary, lies interstellar space. That phrase alone used to sound almost mythical. Interstellar space, the region between stars. For generations it belonged mostly to science fiction and ambitious dreamers, but today humanity has actually touched it. Tiny robotic spacecraft built decades ago are now travelling beyond the outer edge of the Sun's influence. Voyager 1 and Voyager 2, launched in 1977, continue drifting farther into the dark even now. Their computers are less powerful than modern smartphones, and yet they became the first human-made objects to approach the invisible wall surrounding our solar system. There's something deeply comforting about that. Machines built by human hands crossing into the space between stars, while Earth continues spinning quietly beneath sleeping cities and glowing streetlights. Of course, the heliosphere is not a wall in the ordinary sense. If you flew toward it in a spacecraft, you would not suddenly crash into an invisible barrier like a confused bird hitting a clean window. There is no dramatic impact, no cosmic brick wall floating in the dark. Instead, the boundary is gradual, complicated, and constantly shifting. Imagine standing at the shore of an ocean where fresh water slowly mixes with salt water. There is no sharp dividing line. The transition is messy and turbulent. One region slowly becomes another. The same thing happens at the edge of the solar system. The outward pressure of the solar wind eventually weakens as it pushes farther from the Sun. Meanwhile, outside the heliosphere, the galaxy presses inward with its own particles, magnetic fields, and radiation. At some enormous distance, those pressures begin to balance. That balancing point marks the beginning of the boundary region. And what fascinates scientists is not only that the wall exists, but that it protects us. Without the heliosphere, life on Earth might look very different. Interstellar space is filled with cosmic radiation, extremely energetic particles moving through the galaxy at near-light speeds. Some are launched by exploding stars. Others come from black holes, neutron stars, or violent events we still do not fully understand. These particles are dangerous. Not dramatic movie dangerous where people instantly glow green and gain telekinetic abilities. Real dangerous. The kind that damages cells, breaks apart DNA, and increases cancer risk over long periods of exposure. The heliosphere acts as a shield against much of this radiation. Not a perfect shield, certainly. Earth's magnetic field and atmosphere also play enormous roles in protecting life. But the heliosphere forms the first great defensive bubble around the solar system, a giant magnetic cocoon generated by the Sun, which means something rather lovely. Every sunrise you've ever seen has also been helping defend you from the galaxy. That feels almost poetic, though the Sun itself is not trying to be kind. Stars are not sentimental. The Sun produces the solar wind simply because it is a gigantic sphere of nuclear fusion continuously throwing energy outward in all directions. Still, one of the side effects of existing inside a star's bubble is safety. And perhaps that's one reason the boundary around our solar system captures the imagination so strongly. It transforms the solar system from a collection of planets into something more intimate, more enclosed, more homelike. We are not just orbiting a star, we are living inside its atmosphere, a very, very large atmosphere. The farther scientists studied this invisible region, the stranger it became. At first, many assumed the heliosphere would be shaped like a simple sphere, a tidy bubble expanding evenly in every direction. But space rarely cooperates with simple geometry. Data from spacecraft suggests the heliosphere is stretched and distorted by magnetic forces from the galaxy itself. Some scientists compare it to a comet shape with a long trailing tail. Others think it may resemble a croissant, which is possibly the most charmingly French shape ever proposed in astrophysics. Somewhere out there, billions of kilometers away, our solar system may resemble a giant cosmic pastry drifting through interstellar space, which honestly makes space feel slightly friendlier. The reason scientists still debate the shape is because we have never seen the heliosphere directly from outside. Trying to map it is a bit like trying to determine the shape of your house while locked inside it with only a flashlight and a few sensors. Everything must be inferred indirectly. Particle measurements, magnetic field changes, tiny fluctuations in cosmic radiation. It is remarkable, really, that humans can deduce anything about such distant regions at all. A few centuries ago, we barely understood what stars were. Some believed they were holes in a celestial dome letting divine light shine through. Others imagined them as eternal fires fixed to crystal spheres. Now, we are measuring the pressure balance between our star and the galaxy itself. That leap in understanding happened astonishingly fast. And yet, despite all our technology, the outer boundary of the solar system remains eerie and mysterious. Temperatures there become difficult to describe meaningfully because particles are so sparse. The sun itself shrinks into a painfully bright star among countless others. Sunlight becomes weak and thin. If you stood somehow near the outer heliosphere, daylight would no longer resemble day at all. The sun would still outshine every other star, but only as a brilliant point in an overwhelmingly black sky. Earth from that distance would be invisible. Not small. Invisible. Carl Sagan once described Earth in Voyager's famous photograph as a pale blue dot. From the edge of the heliosphere, even that pale dot vanishes into darkness. Every person you've ever known, every city, every song, every argument on the internet, every lost sock, every bedtime story, hidden inside a tiny invisible region near one ordinary star. Sometimes the sheer scale of space sounds frightening at first. Human beings are small creatures with very understandable preferences for warm rooms and nearby snacks. Cosmic distances can feel cold and impersonal, but there's another way to look at it. The heliosphere means that even in the vastness of the galaxy, we carry a kind of home with us. Our star creates a bubble of warmth, light, and protection drifting through interstellar darkness. Inside it, planets orbit peacefully for billions of years. Oceans form, atmospheres survive, living things evolve. Eventually, one species begins building telescopes and wondering where the boundary lies. And maybe that curiosity is one of the most human things imaginable, because once we learned that the wall existed, we immediately wanted to reach it. Not to conquer it exactly. Space has a very reliable way of humbling conquerors, but to understand it, to touch the boundary between home and everything beyond home. That desire led to Voyager. The two spacecraft launched in 1977 during a rare alignment of the outer planets. Their original mission was ambitious enough already: visit Jupiter and Saturn. Then continue onward if possible. Nobody expected them to survive this long, yet decades later, Voyager 1 and Voyager 2 still whisper faint signals back toward Earth from unimaginable distances. Tiny robotic bottles drifting through a cosmic sea, and eventually, after travelling farther than any human-made objects in history, they approach the invisible shoreline around our solar system. What they found there changed how scientists understood the edge of the heliosphere entirely. Because the wall, it turns out, is not calm. It crackles with turbulence, magnetic distortions, sudden changes in particle density, invisible shock waves where the solar wind slows dramatically after racing outward for billions of kilometers. Space at the edge of the solar system behaves less like empty vacuum and more like weather, cosmic weather, which is slightly unfair, really. Earth already has enough weather to deal with. Still, that chaos tells an important story. The boundary is alive with interaction between the Sun and the galaxy. Our star is constantly pushing outward, while interstellar space pushes back. And somewhere between those competing forces lies the frontier humanity has only just begun to explore. As the Voyagers continued outward, instruments recorded sudden drops in solar particles and increases in cosmic radiation. The spacecraft were leaving the Sun's protective bubble, crossing into interstellar space. Not entirely leaving the solar system, interestingly enough. The Oort cloud, a distant shell of icy objects surrounding the Sun, extends vastly farther still. But Voyager had crossed the heliopause, the true edge of the heliosphere itself. Humanity had reached the wall, quietly, without explosions or triumphant orchestras, just two aging spacecraft gliding slowly into the dark while tiny radio signals travelled home across billions of kilometres. There's something beautifully gentle about that achievement. No dramatic flag planting, no grand declarations, only curiosity continuing forward. When most people picture the solar system, they imagine a tidy arrangement of planets circling the Sun in peaceful silence. Mercury close in near the heat, the gas giants farther out, tiny Pluto wandering around the outskirts trying its best not to overhear old arguments about planetary status. Beyond that, many imagine empty space stretching endlessly toward the stars. But the solar system is not floating naked through the galaxy. It is wrapped inside something enormous, a gigantic magnetic bubble created by the Sun itself. A structure so large that every planet, moon, asteroid, comet, and spacecraft humanity has ever built exists deep inside it. Even now, while you listen to this, Earth is moving through that bubble at extraordinary speed, without you feeling the slightest thing. The heliosphere. That's the name scientists gave to this invisible region surrounding the solar system. And although it sounds a little like a futuristic sports stadium or a very expensive spa treatment, it is one of the most important structures in our cosmic neighbourhood. Without it, life on Earth might never have survived long enough to wonder about stars in the first place. The heliosphere begins with the Sun. Not the visible surface we see glowing in the sky, but the Sun's outer atmosphere, called the corona. Strangely enough, the corona is far hotter than the Sun's visible surface. The surface itself sits around 5,500 degrees Celsius, while the corona can reach temperatures of several million degrees. That detail bothered scientists for quite a while because it feels backward. It's a bit like discovering the air above a campfire is somehow hotter than the firewood itself. The exact reasons are still being studied, but those enormous temperatures give particles enough energy to escape the Sun's gravity entirely. Electrons and protons stream outward continuously in all directions. This outflow is the solar wind, and despite the gentle name, the solar wind is astonishingly powerful. At Earth's distance from the Sun, these particles travel roughly 400 kilometers per second on average, sometimes much faster during solar storms. That means material leaving the Sun could travel from London to New York in under 20 seconds, which is slightly faster than most airline baggage systems. The solar wind never stops. Every second of every day, the Sun loses millions of tons of material into space. Yet the Sun is so massive that this constant leakage barely affects it. It would take trillions of years for the Sun to lose a significant portion of its mass this way. Stars are operating on scales that make human numbers feel almost decorative. As the solar wind races outward, it carries part of the Sun's magnetic field with it. This creates a huge magnetic environment surrounding the solar system. The heliosphere is not just made of particles, it is also shaped by magnetism. And magnetism in space behaves very differently from what most of us encounter in everyday life. On Earth, magnetism means refrigerator magnets, compasses, or occasionally discovering that paper clips have formed tiny alliances in desk drawers. In space, magnetic fields can stretch across billions of kilometers and influence the motion of entire clouds of charged particles. The sun's magnetic field twists and spirals outward because the sun rotates while releasing the solar wind. Imagine a spinning garden sprinkler spraying water continuously into the air. The streams curve as the sprinkler turns. The sun does something similar, except instead of water, it releases charged particles moving across interplanetary space. This spiral magnetic structure is called the Parker spiral, named after astrophysicist Eugene Parker, who first described the solar wind mathematically in the 1950s. At the time, many scientists doubted Parker's ideas. The notion that the sun continuously blasted material across the solar system sounded extreme, but observations eventually proved him correct, which must have been deeply satisfying. There are few scientific pleasures greater than politely surviving long enough for reality to confirm your calculations. As the solar wind expands outward, it pushes against the material between stars. Interstellar space is not completely empty. There are atoms drifting there, along with cosmic rays and magnetic fields generated by the galaxy itself. So the heliosphere forms because two enormous pressures meet. The sun pushes outward, the galaxy pushes inward, and somewhere between them, a bubble emerges. That bubble moves with us through the Milky Way like the wake surrounding a ship crossing dark water. The shape of the heliosphere is still debated because it is difficult to measure from inside. Scientists rely on data from spacecraft, particle detectors, magnetic readings, and computer simulations to piece together its structure. Early models assumed the heliosphere resembled a giant comet with a rounded front and a long trailing tail extending behind the solar system as it moves through interstellar space. More recent studies suggest it may be shorter and more compact than originally thought. Some models even suggest a crescent-like shape, influenced heavily by solar magnetic fields. Unfortunately, the universe continues its long tradition of refusing to organize itself into clean textbook diagrams. Still, regardless of the exact shape, the heliosphere is enormous beyond ordinary comprehension. Neptune, the outermost major planet, orbits roughly 30 astronomical units from the Sun. 1 astronomical unit, or AU, equals the average distance between Earth and the Sun. The heliosphere stretches far beyond Neptune, far beyond Pluto, far beyond the Kuiper Belt. The outer boundary, called the heliopause, lies roughly 120 astronomical units from the Sun in some directions, possibly farther in others depending on solar activity and interstellar pressure. To put that in perspective, if Earth were one step away from the Sun, the heliopause would be over a football field away. And even then, you still would not be close to the nearest star. Space is extraordinarily spacious, rather unfairly so. One fascinating thing about the heliosphere is that it changes constantly. The Sun itself operates on an approximately 11-year solar cycle. During periods of high solar activity called solar maximum, the Sun produces more sunspots, solar flares, and coronal mass ejections. The solar wind becomes more turbulent and intense. During quieter periods called solar minimum, solar activity decreases. As these cycles change, the heliosphere expands and contracts slightly like a breathing organism. Not alive, of course. Space physics has enough complexity already without the solar system secretly inhaling. But the bubble is dynamic, flexible, responsive, and Earth exists deep inside that changing environment. Most of the time, we barely notice. Yet occasionally the Sun reminds us. Solar storms can send huge bursts of charged particles toward Earth, disturbing magnetic fields and creating brilliant auroras near the poles. These displays are beautiful from the ground, but potentially dangerous for satellites, astronauts, and power grids. The heliosphere connects all of this together. It is not separate from life on Earth. We are immersed within it completely. In fact, astronauts travelling beyond Earth's magnetic field become far more exposed to radiation from space because Earth's local protection weakens. The heliosphere still shields them somewhat from galactic cosmic rays, but not nearly as effectively as Earth's atmosphere and magnetic field combined. This becomes one of the greatest challenges for future deep space travel. Science fiction often shows interstellar journeys as smooth and glamorous affairs involving elegant starships and very confident captains. Reality is considerably less forgiving. Space radiation is a serious biological problem. The heliosphere quietly helps reduce that danger every day. Galactic cosmic rays are among the most energetic particles in the universe. Some move at nearly the speed of light. They originate from violent cosmic events like supernova explosions. When these particles slam into living tissue, they can damage DNA and cells directly. The heliosphere acts as a partial shield by deflecting many of these particles away from the inner solar system. Not all of them. Some still penetrate the bubble, others collide with Earth's atmosphere and create showers of secondary particles. But without the heliosphere, radiation levels throughout the solar system would likely be much harsher. Which means the Sun, despite being capable of frying spacecraft and occasionally disrupting telecommunications, is also functioning as a gigantic protective barrier against even worse conditions beyond. Stars are complicated neighbours, warm and dangerous at the same time, a bit like owning a fireplace large enough to occasionally launch radiation across several billion kilometres. Scientists only truly began understanding the heliosphere during the space age. Before spacecraft travelled beyond Earth, the existence of the solar wind remained theoretical. Then probes started measuring it directly. One by one, spacecraft revealed that space within the solar system is not calm emptiness, but a flowing environment full of magnetic interactions and charged particles. Pioneer spacecraft explored the outer planets. Voyager expanded humanity's reach farther still. Then came missions like Ulysses, which studied the Sun's poles, and IBEX, the interstellar boundary explorer, which mapped energetic particles near the heliosphere's edge. IBEX made one particularly strange discovery. It found a mysterious ribbon of energetic particles wrapping around part of the heliosphere boundary. Scientists had not predicted this structure beforehand, which is one of the recurring themes of astronomy. Every time humanity points instruments somewhere new, the universe calmly produces something unexpected. The ribbon likely forms because interstellar magnetic fields interact with particles near the heliosphere's outer edge. But researchers still debate exactly how it works. And that uncertainty is important to remember. The heliosphere is not fully understood. Human beings have physically reached its boundary with spacecraft, yet the structure itself remains partly mysterious. We are studying a colossal invisible bubble surrounding our entire solar system while sitting safely inside it. It is rather like fish slowly discovering water. There's another fascinating aspect to the heliosphere as well. It changes depending on where the Sun travels through the galaxy. Right now, our solar system moves through a region called the local interstellar cloud. This cloud is relatively thin and diffuse compared to denser regions elsewhere in the Milky Way. If the Sun eventually enters a denser cloud in the distant future, the heliosphere could compress significantly under the increased external pressure. That might allow more cosmic radiation into the inner solar system. Earth's climate and radiation environment could change over geological timescales simply because the Sun drifts into different galactic neighbourhoods, which is a wonderfully unsettling reminder that even our cosmic surroundings have weather patterns. Galactic weather. And we're riding through it aboard a planet spinning quietly around an ordinary star. The heliosphere also has layers. It is not just one simple shell. Closer to the Sun, the solar wind races outward at supersonic speeds. Eventually, however, it encounters enough pressure from interstellar space that it begins slowing dramatically. This creates a shockwave region called the termination shock. Beyond that lies the heliosheath, a turbulent area where slowed solar wind piles up chaotically before finally reaching the heliopause itself, where solar influence balances against interstellar pressure. Past the heliopause begins true interstellar space. Voyager 1 crossed the heliopause in 2012. Voyager 2 crossed in 2018. These events were historic, though they happened quietly enough that most people were probably busy doing entirely ordinary things at the time. Making coffee, folding laundry, wondering where that one missing charger disappeared to. Meanwhile, tiny spacecraft built in the 1970s slipped beyond the sun's protective bubble. That contrast feels strangely human. The greatest discoveries often occur while the world carries on normally. Even more touching is the fact that Voyager still communicates with Earth across those impossible distances. The signals are faint beyond imagination. Travelling at light speed, each message takes more than 20 hours to arrive. Engineers use enormous radio antennas to detect whispers from spacecraft running on aging systems powered by decaying plutonium. And yet the connection persists, humanity still speaking softly into the dark. There's something deeply comforting about that image, because the heliosphere, enormous as it is, reminds us that home is not merely a planet. Home can also be an environment, a region of influence, a shared protective bubble drifting through the galaxy. Every human civilization in history developed entirely inside the heliosphere. Every war, every invention, every poem, every awkward school presentation, every cup of tea ever nervously carried across a room, all of it happened inside this invisible magnetic shelter surrounding the sun. Most people never think about it because the heliosphere cannot be seen directly with human eyes. There are no glowing borders in the sky, no shimmering dome overhead. But invisibility does not mean insignificance. Air is invisible too, and we become very aware of it the moment it disappears. The heliosphere belongs to that category of cosmic structures quietly shaping our existence without demanding attention. And perhaps that's partly why it feels so fascinating once you learn about it. The solar system suddenly stops feeling isolated. Instead, it feels alive with interaction. The sun pushes outward continuously. Interstellar space pushes back. Magnetic fields twist through darkness. Radiation streams across unimaginable distances. Invisible boundaries form and shift while planets orbit peacefully inside. All of this happening right now while most of us are busy deciding whether we're too tired to wash one more dish before bed. The scale difference between human life and cosmic structure can sound overwhelming at first, yet somehow the opposite feeling often emerges: comfort. Because despite the enormity of the galaxy, we're not entirely exposed to it. We travel together inside the sun's bubble, protected, at least partially, from the harshness beyond. Long before human beings understood what stars really were, the sun already seemed alive. Ancient civilizations worshipped it, feared it, tracked it across the sky, and built entire calendars around its movements. To early people, the sun felt dependable but mysterious. It rose every morning without fail, warmed the land, grew crops, and then vanished each evening into darkness as if following rules only the heavens understood. Yet even the most imaginative ancient astronomers could never have guessed that the sun was continuously throwing part of itself across the solar system. Right now, while Earth quietly turns beneath sleeping cities and drifting clouds, an invisible storm is flowing outward from the sun in every direction. It races past planets, moons, asteroids, and spacecraft. It stretches billions of kilometers into the dark, and eventually, far beyond Pluto, it collides with the pressure of the galaxy itself. This endless stream is called the solar wind, although wind may still be one of the most unintentionally modest terms in astronomy. Earthly wind rustles leaves, bends trees, and occasionally ruins umbrellas with deeply personal levels of aggression. The solar wind carries charged particles moving hundreds of kilometers every second across distances so enormous they barely fit inside the imagination. And unlike ordinary wind, it never truly stops. The sun is breathing constantly. Not breathing air, of course. Space contains far too little matter for that. But in a very real sense, the sun continuously exhales part of its atmosphere outward into space. The heliosphere exists because of this endless outward breath. To understand the solar wind properly, it helps to start with the sun itself. The sun is not burning in the way fire burns on Earth. There is no oxygen involved, no flames licking upward from logs somewhere deep inside. Instead, the sun is powered by nuclear fusion occurring in its core. Every second, around 600 million tons of hydrogen fuse together to form helium. That process releases extraordinary amounts of energy. So much energy, in fact, that a tiny fraction reaches Earth after travelling roughly 150 million kilometres through space, and still powers nearly all life on the planet. Sunlight warming your skin began as fusion deep inside the sun hundreds of thousands of years ago. That detail alone feels slightly unbelievable. The energy produced in the sun's core takes an astonishingly long time to fight its way outward through dense layers of plasma. Photons bounce around endlessly like exhausted commuters trapped in cosmic traffic. Only after immense stretches of time does that energy finally emerge from the sun's visible surface and stream into space. But the solar wind originates higher up. Far above the visible surface lies the corona, the sun's outer atmosphere. During total solar eclipses, the corona becomes visible as a pale glowing halo surrounding the darkened sun. And the corona is deeply strange. For one thing, it is much hotter than the surface below it. The visible surface of the sun sits at roughly 5,500 degrees Celsius. The corona can exceed 1,000,000 degrees. Scientists spent decades trying to understand how that could possibly happen. Heat should normally decrease farther from the source, not increase dramatically. It would be like climbing away from a campfire only to discover the air above the flames is somehow hotter than the flames themselves. The leading explanations involve magnetic fields twisting and reconnecting violently within the corona, releasing tremendous energy into the surrounding plasma. Plasma itself deserves a brief pause here because it behaves differently from ordinary matter. Most of us grow up learning about solids, liquids and gases. Ice, water, steam. Simple enough. But plasma is sometimes called the fourth state of matter. When gas becomes extremely hot, electrons separate from atoms entirely, creating a soup of charged particles. This electrically charged material responds strongly to magnetic fields. The sun is made almost entirely of plasma, which means the sun is not calm. It churns, boils, twists, convects. Immense rivers of plasma rise and fall beneath the visible surface. Magnetic fields knot themselves into bizarre structures. Sunspots appear where magnetic activity temporarily cools parts of the surface. Solar flares erupt when magnetic energy is suddenly released. The sun often looks peaceful from Earth, because our eyes cannot perceive the violence unfolding there. In reality, the sun is a gigantic, unstable sphere of nuclear plasma, behaving like an endless storm. And from that storm comes the solar wind. Because the corona is so hot, some particles gain enough energy to escape the sun's gravity entirely. Once they break free, they stream outward continuously into space. Mostly electrons and protons, tiny charged particles moving at extraordinary speeds. This process happens everywhere across the corona at once. The result is a constant outward flow extending across the entire solar system. When scientists first proposed the solar wind, many researchers doubted the idea. The concept sounded too dramatic. Surely space between planets was mostly empty and static. But observations gradually confirmed the truth. Comets offered early clues. Whenever comets approach the inner solar system, they develop glowing tails. Interestingly, those tails always point away from the sun regardless of the comet's direction of travel. Something was pushing on them continuously. That something turned out to be the solar wind. Later, spacecraft directly measured the flow of charged particles moving outward from the sun. Eugene Parker, the astrophysicist who predicted the solar wind mathematically in the 1950s, was proven correct. Today, the Parker Solar Probe bears his name and flies closer to the Sun than any spacecraft in history, which is a wonderfully intimidating job description. Imagine introducing yourself at parties as the person designing machines that intentionally dive toward a star. The Parker Solar Probe experiences temperatures hot enough to melt most materials humans normally use for construction. Yet its heat shield protects delicate instruments hidden behind it, and those instruments have revealed astonishing details about the solar wind. For one thing, the solar wind is not smooth. There are actually two main types: fast solar wind and slow solar wind. The fast solar wind travels roughly 700 to 800 kilometers per second and tends to emerge from regions called coronal holes, where magnetic field lines open outward into space. The slow solar wind moves closer to 300 to 500 kilometers per second and behaves far more chaotically. Scientists still debate exactly how the slow solar wind forms, which means the Sun continues to keep secrets, despite humanity studying it intensely for centuries. The solar wind also changes depending on the Sun's activity cycle. Every 11 years or so, the Sun's magnetic field flips completely. North becomes south, south becomes north. During this cycle, solar activity rises and falls. At solar maximum, the Sun becomes much more active. Sunspots increase. Solar flares erupt more frequently. Massive clouds of plasma called coronal mass ejections blast into space. These eruptions can contain billions of tons of material. When directed toward Earth, they interact with our magnetic field and atmosphere dramatically. Auroras brighten near the poles. Satellites experience disruptions. Radio communications weaken. Power grids occasionally struggle. In extreme cases, solar storms can become genuinely dangerous for modern technology. One famous example occurred in 1859. The Carrington event, named after astronomer Richard Carrington, remains the most powerful solar storm ever recorded. Telegraph systems across Earth malfunctioned wildly. Operators received shocks. Sparks flew from equipment. Auroras appeared unusually far from the poles, illuminating skies over regions where such displays are almost never seen. Some people reportedly read newspapers outdoors at midnight beneath glowing auroral light. If a similar event struck today, it could disrupt satellites, internet infrastructure, navigation systems, and electrical grids worldwide, which is mildly unsettling considering modern civilization becomes emotionally distressed when Wi-Fi disappears for 6 minutes. Fortunately, Earth possesses powerful protection. Our planet's magnetic field deflects much of the solar wind around us. Charged particles spiral along magnetic field lines toward the poles instead of slamming directly into the atmosphere everywhere equally. Without Earth's magnetic field, the situation would look very different. Mars offers a sobering example. Long ago, Mars likely possessed a thicker atmosphere and liquid water across its surface. But unlike Earth, Mars lost most of its global magnetic field billions of years ago. Without strong magnetic protection, the solar wind gradually stripped much of the Martian atmosphere away. Tiny particles streaming from the Sun slowly eroded an entire planet's climate over immense stretches of time. That idea feels almost unreal. The solar wind sounds intangible and harmless because individual particles are microscopic. Yet over millions and billions of years their effects become enormous. Space operates with astonishing patience. The solar wind also shapes comet tails, influences planetary magnetospheres, and fills interplanetary space with constantly moving plasma. Earth exists inside this flowing environment continuously. The space between planets is not empty stillness, it is weather, cosmic weather, and sometimes that weather becomes turbulent. Coronal mass ejections are especially dramatic examples. During these eruptions, giant loops of plasma and magnetic fields burst outward from the Sun. If one passes over Earth, the interaction with our magnetic field can produce geomagnetic storms. Astronauts must sometimes shelter from increased radiation exposure during such events. airlines occasionally reroute polar flights because high-energy particles can interfere with communications and expose passengers to slightly elevated radiation levels. Meanwhile, millions of people below remain completely unaware that part of a star briefly lashed outward across the solar system. The sun is simultaneously familiar and alien in that way. We see it daily, depend on it absolutely, and yet most of what it truly is remains invisible to ordinary human senses. The solar wind extends far beyond Earth, past Mars, past Jupiter, past Saturn, past every major planet. Even at Pluto's distance, particles from the sun still flow outward through darkness. But eventually, after travelling billions of kilometres, something changes. The solar wind begins to weaken, not because the sun stops producing it, but because the outward pressure decreases with distance. The farther the particles spread, the thinner and less forceful the flow becomes. Meanwhile, beyond the solar system lies interstellar space filled with its own particles and magnetic pressures. The outward-moving solar wind eventually encounters enough resistance from the galaxy that it can no longer maintain its supersonic speed, and there, at immense distances from the sun, the solar wind experiences something extraordinary. It slows down abruptly. This region is called the termination shock. The name sounds slightly ominous, like a forgotten action movie from the 1980s involving astronauts and questionable sunglasses, but scientifically, it refers to a genuine shockwave in space. Shockwaves happen whenever something moving faster than the local speed of waves suddenly slows. On Earth, supersonic aircraft create shockwaves that produce sonic booms. In space, the solar wind generates a colossal invisible version of the same basic phenomenon. Beyond the termination shock lies the heliosheath, where slowed solar wind becomes turbulent and compressed before finally reaching the heliopause itself. And all of this structure exists because the sun never stops breathing outward. That continuous breath forms the entire heliosphere. It protects us partially from galactic cosmic rays. It shapes planetary environments. It creates auroras. It sculpts comet tails. It pushes against the galaxy itself, and it surrounds every human being alive. There's something strangely comforting about imagining Earth floating deep inside the sun's extended atmosphere. Not isolated, not abandoned. Wrapped inside a vast moving magnetic bubble generated by our star. The farther scientists studied the solar wind, the more complex it became. Researchers discovered waves moving through the plasma, magnetic reconnection events, particle acceleration mechanisms capable of boosting charged particles to tremendous energies. Some regions behave almost like oceans with invisible currents and turbulence. Space physics turns out to be astonishingly fluid. The sun's influence reaches farther than ancient astronomers could ever have imagined. For most of history, humanity thought sunlight itself was the main connection between Earth and the sun. Now we know the sun continuously touches every corner of the solar system with streams of plasma and magnetism. Even now, the solar wind is washing over distant spacecraft built decades ago. Voyager 1 and Voyager 2 travelled through it for years before reaching the outer boundaries of the heliosphere. The New Horizons spacecraft crossed through it on its journey toward Pluto and beyond. Every probe leaving the inner solar system must eventually pass through this endless outward flow from the sun. And one of the strangest realizations of all is this: the solar wind is carrying tiny traces of the sun itself outward forever. Particles born near our star drift through darkness across impossible distances. Some may wander the galaxy long after Earth itself is gone. The sun is continuously scattering microscopic fragments of its existence into interstellar space. Not dramatically, quietly, patiently, endlessly. Out beyond the familiar planets, past the graceful rings of Saturn and the blue distances surrounding Neptune, the solar system begins to feel very different. Sunlight weakens, temperatures fall, the planets become sparse, scattered islands drifting through an ocean of darkness so large it almost stops feeling measurable. If you stood somewhere near Pluto, the sun would no longer dominate the sky as it does on Earth. It would appear more like an intensely bright star surrounded by countless others. And still, even that far from home, the sun's influence continues. The solar wind keeps racing outward. Invisible streams of charged particles flow through the dark at supersonic speeds, carrying magnetic fields far beyond the planets. For billions of kilometers, nothing seems capable of stopping that outward rush. But eventually, very slowly, the galaxy pushes back, and somewhere near the outer frontier of the heliosphere, the solar wind encounters a boundary unlike anything closer to the sun. The termination shock. This is the place where the solar wind first begins to lose its dominance. A region where the outward breath of the sun, after racing across enormous distances, suddenly slows from supersonic speeds to something far more turbulent and unstable. The name sounds dramatic, admittedly, slightly like a science fiction thriller involving robots and deeply stressed astronauts. But the physics behind it is real, and surprisingly understandable once we take it step by step. Shockwaves happen whenever something moving faster than the local speed of waves slows abruptly. Here on Earth, we know this phenomenon mostly through sound. When an aircraft exceeds the speed of sound, it creates pressure waves that pile up together. The result is a sonic boom. Air cannot move out of the way fast enough, so the disturbance compresses into a shock wave. The solar wind behaves similarly. Near the sun, the solar wind travels faster than pressure disturbances can move through the surrounding plasma. In other words, it is moving supersonically through space. That detail feels strange at first because most people imagine space as silent emptiness, where concepts like sound become meaningless, and technically, sound as we experience it cannot travel through vacuum because there are too few particles. But the solar wind is plasma, and plasma supports its own kinds of waves through magnetic and particle interactions. Space has its own version of weather physics, and eventually, after travelling billions of kilometres outward, the solar wind encounters enough resistance from interstellar pressure that it can no longer sustain those enormous speeds. At that moment, it slows abruptly. That transition creates the termination shock. The shock itself is not a solid wall. Nothing dramatic or visible hangs in space like a glowing barrier from a science fiction film. A spacecraft crossing the termination shock would not slam into anything physical. Instead, the change happens in the behavior of particles and magnetic fields. The solar wind suddenly becomes denser, hotter, slower, and far more chaotic. Imagine a river flowing rapidly downstream before suddenly entering a crowded marshland where movement becomes turbulent and confused. Water piles up, currents twist unpredictably, smooth flow disappears. Something similar happens at the termination shock, and humanity eventually reached it. That still feels astonishing. For most of history, the termination shock was completely unknown because nobody even realized the heliosphere existed. Then, within a few generations, humans built machines capable of reaching its outer boundaries. Voyager 1 crossed the termination shock in 2004. Voyager 2 crossed in 2007. The distances involved are difficult to truly grasp. Voyager 1 encountered the termination shock roughly 94 astronomical units from the Sun. Voyager 2 crossed around 84 astronomical units out. Remember, 1 astronomical unit equals the distance between Earth and the Sun. These spacecraft had travelled billions upon billions of kilometres through darkness, before reaching the point where the Sun's wind finally began to falter, and even then, they were still inside the heliosphere. That detail matters, because the termination shock is not the end of the solar system's protective bubble. It is more like the beginning of the outer frontier. Beyond it lies the heliosphere, a turbulent region where slowed solar wind churns before eventually meeting interstellar space itself at the heliopause. But the termination shock is where things first start changing dramatically. One fascinating discovery from Voyager was that the shock behaved differently than scientists expected. Researchers initially imagined a relatively clean and stable boundary. Instead, the region turned out to be messy and dynamic, which honestly should probably be astronomy's official slogan by now. Every time humans expect neat simplicity, the universe responds with turbulence. Voyager detected strange fluctuations in particle energies and magnetic fields near the shock. Some particles became accelerated to tremendous speeds. Others behaved unpredictably. The shock itself seemed to move and ripple rather than remaining fixed. Because the sun changes over time, the heliosphere changes too. During periods of stronger solar activity, increased solar wind pressure can push the termination shock outward. During quieter solar periods, the boundary may drift inward slightly. The outer solar system is not static. It breathes and shifts continuously. That idea can feel oddly alive even though these processes are entirely physical. The sun exhales outward. The galaxy presses inward. The boundary flexes between them. One especially important feature of the termination shock involves energy transfer. When the solar wind slows abruptly, enormous amounts of energy must go somewhere. Some of that energy heats the plasma, some accelerates particles to high speeds. Scientists think this region helps generate what are called anomalous cosmic rays, particles accelerated within the heliosphere itself. Space near the termination shock behaves almost like a gigantic particle accelerator. Except instead of being buried underground inside laboratories, it stretches across billions of kilometers at the edge of the solar system, and it operates continuously without needing grant applications or coffee breaks. Another remarkable aspect is how thinly spread matter becomes out there. Even within the solar wind, particles are incredibly sparse compared to conditions on Earth. Near Earth's orbit, there may only be a few particles per cubic centimetre. By the time you approach the termination shock, densities become even lower. Yet despite this extreme thinness, magnetic and plasma effects still dominate behaviour across enormous scales. That is one of the strangest truths about space physics. Tiny numbers become powerful when distances become enormous. Individual particles matter very little. Vast streams of particles crossing billions of kilometres matter enormously. The termination shock also marks a psychological threshold in human exploration. Closer to the sun, space still feels somewhat connected to home. The planets are recognisable neighbours. Sunlight remains relatively bright. Communication delays, while frustrating, stay manageable. Out near the termination shock, however, the solar system begins feeling truly remote. Communication with Voyager takes more than a day each way. If engineers send a command to the spacecraft, they must wait roughly 20 hours or more just for the signal to arrive, then another 20 hours or more for confirmation to return. Simple troubleshooting becomes an exercise in cosmic patience. Imagine trying to fix a device where every question and answer takes nearly 2 days. Have you tried turning it off and on again? 40 hours later, yes. The fact that Voyager still functions at all is extraordinary. These spacecraft launched in 1977. When Voyager began its journey, personal computers barely existed. Mobile phones were enormous rarities. The internet as we know it did not exist. And now those same machines have crossed the termination shock and entered regions no human technology had ever explored before. There's something deeply moving about that continuity, human curiosity travelling patiently outward across decades. The Voyagers carry golden records as well, filled with sounds and images from Earth, greetings in multiple languages, music, natural sounds, tiny time capsules drifting toward the stars. It's strangely comforting that humanity chose to send music into interstellar darkness. Not military plans, not advertisements, music, and whale songs, which honestly feels appropriate. Space and whales both seem to inspire the same mixture of awe and confusion. Near the termination shock, Voyager detected something scientists had hoped to observe directly for years: the slowing of the solar wind itself. particles that once raced outward at supersonic speeds suddenly became sluggish and turbulent. Temperatures increased dramatically. Magnetic fields twisted unpredictably. The spacecraft had reached a genuine transition zone between the Sun's influence and the wider galaxy. Yet even there, the Sun still mattered. That is important to remember. The termination shock does not mean the solar wind stops completely. It only slows and becomes compressed. The Sun's influence continues outward through the heliosheath, all the way to the heliopause. In many ways, the termination shock resembles the bow wave ahead of a ship moving through water. As the solar system travels through interstellar space, interactions build up at the boundary regions. Plasma and magnetic pressures create structures surprisingly similar to fluid dynamics on Earth. The universe repeatedly reuses patterns: rivers, air currents, ocean waves, plasma flows. Similar principles emerge across wildly different environments. That repetition gives physics a certain comforting consistency. Even at the edge of the solar system, nature still follows recognizable rules, though sometimes with significantly larger consequences. One mystery scientists continue studying involves the exact structure of the termination shock itself. Voyager 1 and Voyager 2 crossed the shock at different distances from the Sun. That suggests the boundary is asymmetrical. Why? Likely because interstellar magnetic fields distort the heliosphere unevenly. The galaxy presses harder in some directions than others. The Sun's own changing activity also contributes. The result is a shifting, irregular frontier rather than a perfect spherical shell. And because only 2 spacecraft have crossed it directly, our understanding remains incomplete. 2 tiny probes cannot fully map a structure this vast. Imagine trying to understand the shape of Earth's oceans using only 2 drifting buoys. Still, those buoys would teach you something precious. And Voyager taught humanity that the outer boundary of our solar system is active, dynamic, and surprisingly turbulent. The crossing itself happened quietly. No triumphant fanfare echoed through space. No dramatic visual marker announced the moment. Voyager simply kept drifting forward while instruments recorded changes invisible to human senses. That quietness feels appropriate somehow. The greatest frontiers in science often reveal themselves gradually. A shift in data, a subtle pattern, a whisper from deep space arriving through radio antennas on Earth. And those whispers told scientists something extraordinary. The Sun's influence, vast as it is, eventually weakens, not suddenly, not catastrophically, simply gradually until interstellar space begins asserting itself more strongly. There is something oddly human about that realization. Even stars have limits. The solar wind races outward for billions of kilometers with astonishing power, but eventually the wider galaxy pushes back hard enough to slow it down. The heliosphere is not invincible, it survives through balance. And balance in the universe often creates boundaries. Beyond the termination shock, the solar system changes character once again. The solar wind no longer races outward smoothly at enormous supersonic speeds. Instead, it becomes compressed, heated, and turbulent. The neat outward flow that began near the Sun breaks apart into chaotic currents and magnetic disturbances stretching across billions of kilometers. This strange outer region is called the heliosheath, and if the inner solar system feels somewhat like a calm harbor surrounding the Sun, the heliosheath is more like a stormy coastline where familiar waters begin colliding with a larger and more powerful ocean. It is one of the most remote places humanity has ever explored. Even now, only 2 spacecraft have entered it. Voyager 1 and Voyager 2 crossed into the helioheath after passing through the termination shock, and what they discovered there surprised scientists almost immediately. The region was far stranger than expected. Before Voyager arrived, many researchers imagined the heliosheath as a relatively smooth transition zone. Not empty exactly, but understandable, predictable. Instead, the outer edge of the solar system turned out to be turbulent, restless, and deeply complicated. which by this point was becoming something of a tradition. Space repeatedly refuses to behave politely for astronomers. The heliosheath forms because the solar wind slows dramatically after crossing the termination shock. But even though the wind decelerates, the sun continues pushing outward continuously behind it. More solar wind keeps arriving from the inner solar system. Imagine cars speeding down a highway before suddenly encountering a massive traffic jam. Vehicles continue arriving from behind, but movement ahead becomes increasingly crowded and chaotic. Density builds, motion becomes confused, everything compresses together. The heliosheath behaves similarly. Slowed solar wind piles up against the pressure of interstellar space pressing inward from beyond the heliosphere. The result is a gigantic region of disturbed plasma and tangled magnetic fields surrounding the outer solar system, and the scale of it remains almost impossible to visualize properly. Voyager 1 travelled through the heliosheath for roughly 8 years before finally crossing the heliopause into interstellar space. 8 years. Not 8 years wandering through galaxies or star systems. 8 years crossing the outer turbulent boundary surrounding our own star. That detail alone reveals how immense the heliosphere truly is. Even sunlight begins feeling weak out there. At Earth's distance from the sun, daylight dominates everything, shadows are sharp. The sky glows blue because sunlight scatters through the atmosphere. Near the heliosheath, however, the sun shrinks into an intensely bright point surrounded by blackness. It still outshines every other star, but the warmth and brilliance we associate with sunlight are mostly gone. If Earth suddenly occupied that region, daytime would feel more like permanent twilight. Cold, dim twilight beneath a starry sky, and through that darkness the heliosheath churns invisibly. One fascinating thing scientists discovered is that particles in the heliosheath behave in surprisingly energetic ways. Temperatures there become extremely high. That sounds strange initially because the outer solar system is incredibly cold overall. But temperature in plasma physics often refers to particle motion rather than ordinary human sensations of warmth. The particles themselves move energetically and chaotically even though matter is so sparse that a human body floating there would still freeze almost instantly. Space loves producing combinations that sound contradictory. Hot particles, frozen emptiness, violent turbulence inside near-perfect silence. The heliosheath is filled with magnetic disturbances as well. The sun's magnetic field stretches outward through the solar wind, but once the flow becomes turbulent, those magnetic structures twist and compress unpredictably. Voyager detected fluctuations and strange directional changes in the magnetic field while crossing the region. Scientists realized the heliosheath was not a calm shell at all. It was active, dynamic, almost weather-like. And perhaps weather is genuinely the best analogy. Here on Earth, weather emerges from energy moving through fluids. Warm air rises, cold air sinks, pressure systems collide, turbulence forms. The heliosheath behaves similarly, except the fluid is plasma shaped by magnetic fields across billions of kilometers. Cosmic weather at the edge of the solar system. One especially mysterious discovery involved energetic particles trapped and accelerated within the heliosheath itself. Some particles bounced around the tangled magnetic fields, gaining tremendous energy in the process. Voyager measured strange bursts of radiation scientists had not fully predicted beforehand. In some regions, the intensity of energetic particles increased dramatically. In others, it dropped unexpectedly. The heliosheath seemed filled with invisible structures and boundaries hidden within the larger boundary itself. And perhaps that makes sense. Boundaries in nature are rarely simple. Earth's shorelines shift with tides and storms. Atmospheric fronts twist unpredictably. River deltas branch into complicated networks. Why should the edge of the solar system be any tidier? The farther researchers studied the heliosheath, the more it resembled an enormous turbulent mixing zone where solar influence and interstellar pressure battled continuously. Another remarkable feature of the heliosheath is how asymmetrical it appears to be. Voyager 1 and Voyager 2 entered the heliosheath at different distances from the Sun and crossed the heliopause years apart. That means the heliosphere itself is distorted. The galaxy pushes unevenly against it. Interstellar magnetic fields likely squeeze parts of the heliosphere more strongly than others. Meanwhile, the Sun's changing activity causes additional fluctuations. The result is not a perfect bubble but an irregular moving structure shaped by both internal and external forces, rather like trying to inflate a balloon while someone presses against one side with their hand. And all of this is happening while the entire solar system moves through the Milky Way at enormous speed. The Sun orbits the centre of the galaxy at roughly 828,000 kilometers per hour. Earth spins around the Sun. The Moon circles Earth. The heliosphere rides along with us through interstellar space, like the bow wave surrounding a ship crossing dark water. Sometimes it helps to pause and remember that. Right now, you are not sitting still. None of us are. Every human being alive is travelling together inside this moving magnetic bubble generated by the Sun. Even while sleeping peacefully in bed, you are orbiting, rotating and drifting through the galaxy at astonishing speed. And far beyond the planets, the heliosheath marks the region where our star's influence begins seriously struggling against the wider cosmos. There's something strangely emotional about that idea. The heliosphere feels almost protective, familiar, like a vast invisible shelter surrounding home. The heliosheath is where that shelter becomes thin and unstable, where the outside begins pressing inward harder. Voyager's journey through this region became one of humanity's greatest scientific adventures, precisely because nobody knew exactly what waited there. The spacecraft themselves are wonderfully humble by modern standards. Their computers possess vastly less processing power than ordinary smartphones. Their memory capacity is tiny. Their systems were designed in an era when computers often occupied entire rooms and looked faintly offended by human interaction. Yet those same spacecraft travelled farther than anything humanity had ever built. There's something deeply encouraging about that. Exploration does not always require perfection. Sometimes it requires persistence. Voyager kept going, year after year, decade after decade, through the outer planets, past Pluto's orbit, across the termination shock, into the heliosheath. And all the while, faint radio signals continued whispering back toward Earth across impossible distances. The communication delays became extraordinary. Signals travelling at light speed still required nearly an entire day to cross the gulf between Voyager and Earth. And yet humanity listened patiently. Huge radio antennas captured tiny whispers from spacecraft drifting through the turbulent frontier surrounding the solar system. It feels almost intimate somehow. A species on one small planet quietly maintaining conversation with its distant machines at the edge of interstellar space. One particularly surprising observation involved the behaviour of the magnetic field near the heliopause. Scientists expected a dramatic directional change when Voyager approached the edge of the heliosphere. Instead, the magnetic field remained oddly aligned. This confused researchers for years. Why did the boundary not behave as expected? Eventually, scientists realised the interstellar magnetic field outside the heliosphere may already align somewhat with the Sun's magnetic field near the boundary region. The galaxy itself was shaping conditions around our solar system in ways nobody fully appreciated beforehand. That realisation made the heliosheath even more fascinating. It was not simply the outer edge of the Sun's territory. It was a mixing region between stellar and galactic environments, the place where our local neighbourhood blends into the wider Milky Way. And despite its enormous scale, the heliosheath is still fragile in a sense. If the Sun travelled through denser interstellar clouds in the future, the heliosphere could compress dramatically. The heliosheath might shrink, cosmic radiation levels inside the solar system could increase. Earth's environment is influenced not only by our own star, but by where that star happens to drift through the galaxy, which means the solar system itself experiences changing galactic climates over millions of years. That idea feels wonderfully enormous. Human history spans only tiny slices of time compared to these cosmic motions. Entire civilizations rise and fall while the sun barely shifts position within the Milky Way. Meanwhile, the heliosheath continues churning silently at the frontier of the solar system. Most people will never think about it, and honestly, that is understandable. Daily life already contains enough concerns without adding turbulent plasma boundary near interstellar space to the average grocery list. Still, learning about the heliosheath changes the emotional shape of the solar system slightly. The planets stop feeling isolated. Instead, they feel enclosed together within something larger, a shared environment, a moving bubble, a magnetic cocoon carved into the galaxy by the sun's endless outward breath. And near the edges of that cocoon lies a restless, turbulent sea where the sun slowly begins surrendering control. The heliosheath also serves as a reminder that the universe rarely contains clean borders. Human beings love boundaries, countries, maps, lines, labels. We prefer the comfort of certainty, but nature tends to blur edges instead. Atmospheres fade gradually into space, rivers merge into oceans, forests transition into grasslands through shifting ecological zones rather than sudden walls. The heliosheath follows that same pattern. It is not a neat dividing line, it is a transition, a vast, unstable region where one environment slowly becomes another. For billions of kilometers, the sun holds its ground. Its particles stream outward continuously. Its magnetic field stretches through darkness far beyond the planets. The solar wind races across the solar system, carrying energy, pressure, and fragments of the sun itself into deep space. Then, gradually the outward force weakens. The solar wind slows after crossing the termination shock. It churns turbulently through the heliosheath. The farther it travels, the harder interstellar space pushes back against it. And eventually, after an almost unimaginable journey outward from the sun, a balance is reached. The heliopause. This is the true edge of the heliosphere, the actual boundary separating the sun's domain from the wider galaxy beyond. Not the edge of the solar system entirely, technically speaking. Objects influenced by the sun's gravity extend much farther out, especially within the distant Oort cloud. But the heliopause marks something arguably more meaningful. It is the point where the sun's outward wind can no longer dominate the surrounding interstellar medium. Beyond this invisible frontier begins genuine interstellar space. Humanity reached that boundary only recently. And when we finally crossed it, the moment arrived quietly. No giant wall appeared in the darkness. No shimmering energy field blocked the way. No cosmic border guards demanded paperwork from Voyager. Instead, the transition revealed itself through data. Subtle changes, particle counts, magnetic readings. Tiny whispers from distant instruments travelling across billions of kilometres back toward Earth. And those whispers told humanity something extraordinary. We had reached the edge of our star's protective bubble. The heliopause forms because two enormous pressures meet and eventually balance each other. Inside the heliosphere, the solar wind pushes outward from the sun. Outside, interstellar space presses inward. The interstellar medium contains gas, dust, magnetic fields, and cosmic rays drifting through the galaxy. Sparse though it is by earthly standards, it still exerts pressure. At the heliopause, those opposing forces reach equilibrium. The solar wind can push no farther effectively. The galaxy refuses to yield further. And so a boundary emerges, not solid, not visible, but real. One of the strangest things about the heliopause is that although it represents the edge of the sun's direct influence, it remains incredibly difficult to define sharply. Nature rarely creates perfect borders. Think about coastlines on Earth. Where exactly does land become sea? Waves move constantly, tides shift, sand rearranges itself. The transition is dynamic rather than fixed. The heliopause behaves similarly. It moves slightly depending on solar activity and changes in interstellar pressure. During periods of stronger solar wind, the heliopause may expand outward. During quieter periods, it may contract inward somewhat. The entire heliosphere breathes gently with the rhythm of the sun's activity cycle, and out there near the edge the galaxy pushes back continuously. The result is a living boundary. Not alive biologically, of course. Space already contains enough mysteries without the solar system secretly developing opinions. But the heliopause is active, responsive, changing. Voyager 1 became the first human-made object to cross the heliopause in August 2012. The spacecraft was roughly 121 astronomical units from the Sun. That distance is so large it almost stops feeling meaningful numerically. Light itself, travelling at the fastest speed possible in the universe, required over 16 hours to cover the gap between Voyager and Earth at the time, and yet Voyager kept going. Tiny, ancient, persistent. The crossing itself puzzled scientists initially. Researchers expected a dramatic shift in magnetic field direction upon entering interstellar space, but the magnetic field measured by Voyager remained unexpectedly similar on both sides of the boundary. For a while, confusion spread through the scientific community. Had Voyager truly crossed the heliopause or not? The answer eventually became clear through particle measurements. Inside the heliosphere, solar particles dominate. Outside, galactic cosmic rays increase sharply while particles from the solar wind decline dramatically. Voyager observed exactly that transition. The spacecraft had entered interstellar space. Humanity had crossed the true border surrounding the Sun. There is something deeply emotional about that achievement when you pause long enough to think about it. For almost all of human history, the stars were unreachable lights in the distance. Then, within a few generations, we learned what stars actually are, built machines capable of leaving Earth, explored the planets, and finally reached the edge of the Sun's bubble itself. A species that once feared eclipses now sends robotic emissaries into interstellar darkness, quietly, patiently, without fully realizing how astonishing that really is. Voyager 2 crossed the heliopause in 2018 at a slightly different distance from the Sun than Voyager 1. That detail revealed something important. The heliosphere is asymmetrical. Its shape changes depending on direction because interstellar magnetic fields and particle pressures are uneven around the solar system. Again, the universe refused to provide a neat spherical bubble. Instead, our cosmic neighbourhood possesses wrinkles, distortions, and shifting contours, which honestly makes it feel more real somehow. Perfect shapes belong mostly to textbooks. Actual nature tends to be messier. The heliopause also acts as a partial shield against galactic cosmic rays. This shielding role is enormously important. Beyond the heliosphere, cosmic radiation becomes far more intense. High-energy particles launched by supernova explosions and other violent cosmic events travel through interstellar space at nearly light speed. The heliosphere deflects many of these particles away from the inner solar system. Not all of them. Some still penetrate inward. But Voyager observed a clear increase in galactic cosmic rays immediately after crossing the heliopause. Outside the Sun's protective bubble, the galaxy feels harsher, more exposed, and that realization subtly changes how we think about home. Earth is not merely protected by its atmosphere and magnetic field. The entire solar system exists inside layers of shielding. First Earth's atmosphere, then Earth's magnetic field, then the heliosphere itself, nested protections surrounding one small world orbiting one ordinary star. Without those protections, life would face a far more hostile cosmic environment, which makes the heliopause feel strangely comforting despite its remoteness. The boundary exists because the Sun continuously fights against the wider galaxy on our behalf. Not intentionally, certainly. Stars do not care in the human sense. The sun produces the solar wind naturally because of the physics governing hot plasma and magnetic fields. Still, one consequence of living near a star is protection, a giant magnetic bubble surrounding everything we know. One fascinating aspect of the heliopause is that temperatures there become difficult to discuss meaningfully. The particles in the region may possess enormous energies corresponding to very high temperatures. Yet matter is so incredibly sparse that a human floating there would not feel heat in any ordinary sense. There are simply too few particles transferring energy directly. Space repeatedly reminds us that our everyday intuitions evolved for Earth, not interstellar physics, hot emptiness, frozen radiation, invisible storms. The cosmos enjoys combinations that sound contradictory. Beyond the heliopause lies the local interstellar medium. This region between stars is not empty vacuum but thin gas mixed with dust, magnetic fields, and cosmic rays. The Sun currently travels through a region called the local interstellar cloud. Compared to conditions on Earth, this cloud is extraordinarily diffuse. Yet on galactic scales, it matters enormously. The pressure from this interstellar environment shapes the heliosphere itself. In a sense, the heliopause is where two weather systems meet. Solar weather flowing outward from the Sun, galactic weather pressing inward from interstellar space. And the frontier between them stretches across billions of kilometers around the solar system. Voyager's discoveries near the heliopause transformed our understanding of this region. Scientists found evidence for plasma waves caused by disturbances travelling through interstellar material. They measured unexpected magnetic alignments. They observed dramatic shifts in particle populations. The boundary was not simple at all. It behaved more like a complicated interaction zone filled with dynamic structures and changing conditions. One especially fascinating discovery involved the hydrogen wall. Near the heliopause, interstellar hydrogen atoms pile up because of interactions with the solar wind. This creates a dense region of hot hydrogen surrounding the heliosphere. Essentially, the solar system develops a kind of bow wave while moving through the galaxy. That image feels wonderfully nautical. Our star sailing through interstellar darkness surrounded by invisible waves and magnetic turbulence. The heliopause also raises difficult questions about future interstellar travel. Humanity has barely begun exploring beyond the heliosphere. Voyager itself travels relatively slowly compared to the immense distances between stars. Even at roughly 17 kilometers per second, Voyager 1 would require over 40,000 years to approach another star closely. Interstellar space is vast, almost beyond comprehension. Science fiction often compresses those scales dramatically, because otherwise many stories would involve astronauts spending 6 generations waiting to arrive somewhere. Reality is less convenient. The heliopause marks the beginning of truly enormous distances, and yet humanity crossed it anyway. That matters, because exploration changes perspective. Before Voyager, interstellar space was mostly theoretical abstraction. After Voyager, it became a place humanity had physically entered. A tiny step cosmically, perhaps, but emotionally enormous. There's something profoundly moving about the fact that the first objects to cross the heliopause were not warships or luxury vessels or grand monuments. They were scientific probes, machines built to learn, carrying instruments, cameras, and golden records filled with sounds from Earth. One spacecraft carries greetings in 55 languages. Another carries music ranging from Bach to Chuck Berry. It is difficult not to love a species that encounters the infinite dark between stars and decides to send jazz into it. The farther Voyager travels beyond the heliopause, the weaker its signals become. Its power supply slowly decays. Engineers shut down non-essential systems gradually to conserve energy. Someday the spacecraft will finally fall silent. But even then, it will continue drifting, outward forever, long after Earth's current civilizations are gone, long after modern languages change beyond recognition. Voyager will still move quietly through interstellar darkness, carrying traces of humanity into the galaxy. And it all began by crossing the heliopause, crossing the invisible wall surrounding our solar system. The heliopause also reminds us of something psychologically important. Human beings often imagine space exploration as a process of visiting planets and stars individually. But the heliosphere reveals that our solar system is itself an environment, a moving territory carved into the galaxy by the sun. The heliopause is the shoreline around that territory, the edge of home. There's a subtle emotional shift that happens once you understand this. The solar system stops feeling like isolated objects floating randomly in space. Instead, it becomes connected, unified inside one giant magnetic structure. Mercury, Earth, Jupiter, Pluto, the Voyagers, comets drifting through darkness, all together inside the heliosphere, and beyond the heliopause lies the wider galaxy waiting outside. Sometimes astronomy feels distant from ordinary human life because the scales are so enormous, but the heliopause changes that feeling slightly. Right now, every human being alive exists inside this protective stellar bubble. Every argument, every celebration, every late-night conversation, every child learning the names of planets, all of it unfolding deep inside the sun's invisible territory. The heliopause is the border around all of that, and although it lies billions of kilometers away, it surrounds us constantly. Perhaps that is why the idea feels so strangely intimate despite its scale. Just outside the heliopause, beyond the protective bubble inflated by the sun, the galaxy begins pressing against us directly. Not dramatically, not with explosions or roaring storms or some giant visible barrier dividing one region from another. Space remains dark and mostly silent there. The stars still shine steadily in every direction. A human observer drifting near the boundary would not suddenly see glowing walls stretching across the heavens like something from a science fiction film. And yet something strange exists there. Something scientists call the hydrogen wall. The name sounds almost poetic at first, although the physics behind it is surprisingly practical. Like many discoveries in astronomy, the hydrogen wall emerged not because someone went looking specifically for it, but because instruments detected behavior that made no immediate sense, and what they eventually realized was extraordinary. Our solar system appears to be moving through the galaxy in such a way that interstellar hydrogen piles up around the outer boundary of the heliosphere. In simple terms, the sun's giant magnetic bubble creates a kind of traffic jam in space, which may be the universe's way of reminding us that congestion follows humanity absolutely everywhere, even between stars. To understand the hydrogen wall properly, it helps to think again about motion. The solar system is not stationary. The sun, along with every planet orbiting it, travels through the Milky Way at enormous speed. We're moving through the local interstellar medium continuously, like a ship crossing dark water. As the heliosphere pushes outward against interstellar gas, interactions begin occurring near the outer boundary. Hydrogen atoms drifting through interstellar space become compressed and heated around the front edge of the heliosphere. That compressed region forms the hydrogen wall. It is not a wall in the ordinary sense. No solid barrier exists there. You could pass through it physically without striking anything hard. The atoms remain extraordinarily sparse compared to earthly environments. But on cosmic scales, the increase in hydrogen density matters enormously. And more importantly, it glows, very faintly. Hydrogen atoms absorb and re-emit ultraviolet light from the sun, creating a subtle signature detectable by spacecraft instruments and telescopes. That glow became one of the clues revealing the true structure of the heliosphere. Scientists first suspected the hydrogen wall through observations of distant stars. Ultraviolet light passing through the region showed absorption patterns indicating heated hydrogen surrounding the solar system. Eventually, researchers realized they were observing a compressed shell of interstellar material piled up near the heliopause itself, a bow wave around our cosmic neighborhood. There is something deeply beautiful about that image. The solar system sailing through the galaxy surrounded by invisible currents and faint glowing hydrogen. The farther humanity studies space, the more dynamic it becomes. The old idea of space as empty stillness keeps dissolving. Instead, the universe behaves more like an ocean. Particles flow, magnetic fields twist. Radiation streams through darkness, shockwaves ripple across billions of kilometers, and around our solar system, interstellar hydrogen gathers softly near the boundary, where the sun's influence begins giving way to the galaxy beyond. One especially fascinating aspect of the hydrogen wall is that it may help scientists study astrospheres around other stars. The heliosphere is only our local example of a broader phenomenon. Other stars likely create their own giant magnetic bubbles through stellar winds interacting with interstellar space. Around those stars, hydrogen walls may form as well, which means countless stellar systems across the Milky Way could be travelling through the galaxy, wrapped inside their own invisible cocoons, some perhaps larger than ours, some weaker, some compressed by denser interstellar regions. Every star carrying its own protective bubble into the dark. That realization changes how you imagine the galaxy. Instead of isolated stars floating independently, the Milky Way becomes filled with overlapping spheres of influence moving through interstellar currents like glowing jellyfish drifting through a deep ocean. A slightly terrifying comparison perhaps, though also oddly charming. The hydrogen wall itself marks only the beginning of the true interstellar medium beyond the heliopause, and once Voyager crossed into that region, humanity encountered something psychologically strange. The space between stars turned out not to be empty silence, but it also was not what science fiction often imagines. There are no swirling nebula clouds immediately outside the heliosphere, no giant glowing colours surrounding the solar system, no dramatic cosmic scenery waiting just beyond the edge. Interstellar space is far subtler than that. Darker, colder, more diffuse, and in some ways, lonelier. The nearest stars remain unimaginably distant even after crossing the heliopause. Voyager entered interstellar space in 2012, yet it will require tens of thousands of years to approach another stellar system meaningfully. That fact is difficult for the human mind to sit with comfortably. We evolved in a world where movement produces visible change quickly. Walk long enough and you reach another village. Sail far enough and eventually land appears. Interstellar space does not behave that way. You can travel for years beyond the heliosphere and still remain astonishingly far from any star. The darkness between stars is enormous, and yet it is not truly empty. The interstellar medium contains gas and dust spread thinly across vast distances. Most of it is hydrogen. Tiny traces of heavier elements drift there too, leftovers from ancient stars that exploded long before the sun existed. Every atom in your body heavier than hydrogen originated inside stars. Carbon, oxygen, iron, calcium, all forged through stellar fusion or supernova explosions. Which means interstellar space contains the raw ingredients of future worlds. The galaxy recycles itself continuously. Stars form, burn, die, scatter material outward. New stars emerge later from those remnants, and drifting through the darkness beyond the heliopause are atoms older than Earth itself, older than the Sun perhaps, particles wandering the galaxy for unimaginable stretches of time before briefly passing near our solar system. That thought carries a strange emotional weight. The air you breathe contains atoms that once drifted between stars. Space is not disconnected from us. We are made from it. Voyager's instruments revealed dramatic changes after crossing the heliopause. Inside the heliosphere, solar particles dominate the environment. Outside, galactic cosmic rays become far more intense. The galaxy beyond the sun's protective bubble feels harsher, more exposed. Radiation levels increase noticeably. magnetic fields behave differently. The influence of the sun weakens dramatically. And yet one surprising thing remained. The interstellar magnetic field beyond the heliopause appeared more closely aligned with the heliosphere's magnetic field than scientists expected. This puzzled researchers initially because they anticipated a stronger directional mismatch. Instead, the boundary between solar and galactic influence seemed oddly smooth in magnetic terms. The universe once again refused to provide clean dramatic separations. Nature prefers gradients, transitions, blended edges. One particularly eerie realization about interstellar space involves sound, or rather, the absence of it. Space beyond the heliopause is effectively silent to human ears because sound waves cannot propagate through such thin matter the way they do in air. Even enormous events unfold in silence there. Shock waves ripple through plasma invisibly. Magnetic turbulence twists through darkness. Radiation streams outward from distant stars. All without sound. And perhaps that silence is partly why interstellar space feels emotionally unsettling to people. Human beings are deeply auditory creatures. We associate silence with isolation instinctively. Yet in another sense, interstellar space is not entirely silent. Voyager detected plasma waves beyond the heliopause caused by disturbances moving through the interstellar medium. Scientists converted those plasma oscillations into audio frequencies humans could hear. The resulting sounds are haunting. Soft rising tones, alien whistles, the music of particles vibrating between stars. Not true sound in the ordinary sense, but translated signals from the interstellar medium itself. The galaxy humming quietly beyond the solar system. There's something profoundly intimate about that. Humanity reaching beyond the heliosphere and listening to the vibrations of interstellar plasma. The farther we explore space, the stranger reality becomes. Another fascinating feature of interstellar space is how cold it is. Temperatures vary depending on local conditions, but many regions approach only a few degrees above absolute zero. Absolute zero represents the coldest temperature physically possible, where atomic motion reaches its minimum. And yet even in those frozen regions, particles continue drifting. Magnetic fields continue threading through darkness. Cosmic rays continue racing across the galaxy at nearly light speed. Space is never truly still. Even the emptiness between stars remains active. The darkness beyond the heliopause also changes our perspective on the sun itself. From Earth, the sun dominates existence. It controls our days, weather, climate, and biology completely. Every ancient civilization centered life around it naturally, because survival depended on sunlight. But once you cross into interstellar space, the sun becomes only one star among many. Still brighter than others nearby, certainly. Yet no longer overwhelming. That transition feels emotionally important somehow. Inside the heliosphere, we live within the sun's kingdom. Outside it, the sun joins the wider galactic population. Just another star drifting through the Milky Way, though admittedly one we are rather fond of personally. And beyond the heliopause lies not merely darkness, but distance on scales almost impossible to emotionally process. The nearest star system, Alpha Centauri, lies over 4 light-years away. Voyager 1 moves incredibly fast by human standards, yet it would still require over 70,000 years to pass anywhere near that system. Human civilization itself is younger than that, which means Voyager entered interstellar space not as a traveller nearing another destination, but as the first tiny step into a vastly larger ocean. An ocean so enormous that humanity has barely touched its shoreline, and yet touching the shoreline matters. Because psychologically, crossing the heliopause transformed interstellar space from abstraction into reality. Before Voyager, no human-made object had ever entered the medium between stars. Now one has. Actually 2. That changes something subtle but important inside the human imagination. The galaxy no longer feels entirely unreachable. Difficult beyond comprehension? Yes. Dangerous certainly. Enormous almost beyond language, but not unreachable. The hydrogen wall and the interstellar medium beyond it also remind us how temporary cosmic environments can be. The Sun currently moves through a relatively thin interstellar cloud. In the distant future, it may drift into denser regions of the galaxy. When that happens, the heliosphere could shrink dramatically under increased external pressure. The hydrogen wall would change shape. Cosmic ray penetration into the solar system might increase. Earth's radiation environment could shift over geological timescales simply because our star entered a different galactic neighbourhood. Galactic climate influencing planetary conditions. The scales involved are staggering. Human concerns become wonderfully small beside them sometimes, and perhaps that is part of why astronomy feels calming to so many people. The universe places our anxieties into perspective without dismissing them entirely. Your worries still matter. Your life still matters. But somewhere beyond Pluto, beyond the heliopause, beyond the hydrogen wall, the galaxy continues unfolding according to patterns so vast they gently loosen the grip of everyday stress. The stars do not rush. Interstellar space certainly does not rush. Everything there moves patiently across immense spans of time. In the summer of 1977, humanity launched 2 machines into the dark with no guarantee they would survive even the beginning of their journey. Their names were Voyager 1 and Voyager 2. At the time, nobody imagined they would become the first human-made objects to leave the Sun's protective bubble and enter the space between stars. Their original mission was ambitious enough already. Visit the giant outer planets, send photographs home, study strange moons and storms and magnetic fields, then continue onward for as long as possible. What happened afterward became one of the greatest exploration stories in human history. Even now, nearly half a century later, both spacecraft are still travelling outward through interstellar space. Tiny robotic travellers carrying fragments of humanity into the galaxy. And perhaps the most extraordinary part is how ordinary they look. Voyager spacecraft are not sleek silver starships shaped like science fiction dreams. They do not possess glowing engines or artificial gravity or dramatic rotating sections where people pace thoughtfully while staring through giant windows. They look practical, functional, a little awkward, honestly. Large dish antennas sit above clusters of scientific instruments attached to long metal arms. Wires, booms, and sensors protrude in various directions, with the unmistakable appearance of machines designed by engineers who care deeply about physics and very little about cinematic elegance, which somehow makes them more lovable. Voyager 2 launched first on August 20th, 1977. Voyager 1 launched shortly afterward on September 5th. The numbering seems backward because Voyager 1 travelled faster and followed a slightly different trajectory, allowing it to overtake Voyager 2 early in the mission. And from the beginning, timing mattered enormously. The spacecraft launched during a rare planetary alignment that occurs roughly once every 176 years. The giant outer planets lined up in such a way that spacecraft could use gravitational assists to slingshot from one planet to the next. Gravity assists remain one of the cleverest tricks humans ever discovered for exploring space. Instead of carrying impossible amounts of fuel, a spacecraft approaches a moving planet carefully and steals a tiny fraction of the planet's orbital momentum. The planet loses an almost undetectable amount of energy. The spacecraft gains tremendous speed. It is cosmic pickpocketing on a very polite scale. Using this technique, Voyager could visit multiple outer planets with far less fuel than would otherwise be required. And so, the journey began. At first, the Voyagers explored worlds humanity had barely glimpsed before. Jupiter came first. The photographs sent home transformed astronomy almost immediately. Before Voyager, Jupiter's moons appeared mostly as blurry points of light through telescopes. Then suddenly humanity saw volcanic eruptions on Io, frozen crusts on Europa, and giant swirling storms larger than Earth itself. The solar system became real in an entirely new way. Io especially stunned scientists. Voyager discovered active volcanoes erupting across its surface, making Io the first world beyond Earth known to possess active volcanism. That revelation changed planetary science overnight. Until then, many researchers assumed small moons would be geologically dead, cold, quiet, frozen forever. Instead, Jupiter's gravity flexed Io constantly through tidal forces, heating its interior enough to melt rock and drive eruptions. The universe once again refused to be boring. Europa proved equally fascinating. Beneath its cracked, icy surface lay strong evidence for a hidden ocean, an ocean under ice, on a moon orbiting a giant planet hundreds of millions of kilometers from Earth. Today, Europa remains one of the most promising places in the solar system to search for extraterrestrial life. Voyager helped reveal that possibility. Saturn came next. Its rings, already beautiful through telescopes, became breathtaking in Voyager's images. Thousands of ringlets, strange structures, tiny moons shepherding particles through gravitational interactions, and Titan. Saturn's largest moon appeared wrapped in thick orange haze, hiding its surface entirely. Scientists later learned Titan possesses lakes and rivers of liquid methane beneath that atmosphere, an alien world with weather systems and hydrocarbon rain. All of these discoveries emerged because two spacecraft launched in the 1970s kept travelling outward. Voyager 2 continued farther still. It became the only spacecraft ever to visit Uranus and Neptune. That fact alone still feels astonishing. Humanity has explored those planets exactly once. Once. Voyager 2 remains our only visitor there. Uranus appeared pale blue-green and strangely tilted, rotating almost sideways relative to its orbit. Neptune revealed enormous storms and unexpectedly powerful winds, and Triton, Neptune's moon, displayed nitrogen geysers erupting from its frozen surface. Even at the far edge of the planetary system, the universe remained active and strange. By the late 1980s, the primary planetary mission had ended. The spacecraft had succeeded beyond expectations already, but they kept going, outward, beyond the planets, beyond the familiar solar system, and gradually the mission transformed into something entirely different. The Voyagers became explorers of the heliosphere itself. At this point, the distances involved grew almost impossible to imagine emotionally. Light from the sun required hours to reach the spacecraft. Radio signals travelling between Earth and Voyager took nearly a full day. And still, the probes continued drifting farther into darkness at extraordinary speed. Voyager 1 travels roughly 17 kilometers every second. That is fast enough to cross the continental United States in only a few minutes. Yet on interstellar scales, even that speed feels painfully slow. Space is enormous in ways that human intuition struggles to process comfortably. Still, the Voyagers persisted, and the farther they travelled, the stranger their environment became. The solar wind weakened gradually with distance. Charged particles from the sun became more sparse. Magnetic fields shifted. Cosmic radiation increased. Then came the termination shock. Voyager 1 crossed it in 2004. Voyager 2 crossed in 2007. The spacecraft had entered the heliosheath, the turbulent outer frontier of the heliosphere where the sun's wind slows and becomes chaotic under pressure from interstellar space. This region turned out to be far more complicated than scientists expected. Particle behavior fluctuated unpredictably. Magnetic fields twisted strangely. Radiation levels shifted dramatically. The edge of the solar system behaved less like a neat boundary and more like a stormy coastline, and beyond it lay the heliopause. The true border between the sun's magnetic bubble and interstellar space itself. Voyager 1 crossed the heliopause in 2012. Humanity had officially entered interstellar space for the first time. That sentence still carries emotional weight. Not astronauts, not giant starships. A small robotic probe launched decades earlier crossed into the space between stars, while most of humanity was busy living ordinary lives on Earth. Working, cooking dinner, walking dogs, paying bills. Meanwhile, one tiny machine built by human hands slipped beyond the solar system's protective bubble. The crossing revealed itself through data rather than spectacle. Solar particles dropped sharply. Galactic cosmic rays increased. The spacecraft had moved beyond the sun's dominant influence. Interstellar space had begun. Voyager 2 crossed the heliopause in 2018, confirming many of the earlier observations while revealing additional complexities. The heliosphere's boundary proved asymmetrical and dynamic. Conditions differed depending on location and solar activity. The galaxy outside pressed unevenly against the solar system. The Voyagers taught humanity that our cosmic neighborhood is alive with interaction. And remarkably, both spacecraft still function today. Barely, admittedly. Their power supplies weaken every year because they rely on radioactive plutonium gradually decaying over time. Engineers carefully shut down instruments one by one to conserve electricity. The spacecraft are old. Very old. Their computers contain vastly less processing capability than modern household appliances, yet they continue operating in one of the harshest environments imaginable. There's something deeply inspiring about that resilience. The Voyagers were designed during an era when engineers expected hardware to last, possibly because replacing it involved launching rockets across the solar system, which tends to discourage casual upgrades. Communication with Voyager now requires extraordinary precision. The signals arriving at Earth are unimaginably faint. By the time Voyager's radio transmissions reach us, the signal strength is roughly comparable to the energy output of a refrigerator light bulb spread across billions of kilometers, and yet giant radio antennas on Earth still hear those whispers. The Deep Space Network, a global system of enormous radio dishes, listens continuously for signals from humanity's distant travelers. There's something almost tender about that image. Civilization quietly listening across the dark for the voices of its machines. The Voyagers also carry perhaps the most famous time capsules ever created, the Golden Records. Attached to each spacecraft is a gold-plated copper disc containing sounds and images from Earth selected by a team led by Carl Sagan. The records include greetings in 55 languages, music from different cultures, natural sounds from Earth, rain, thunder, birdsong. Whale calls, a heartbeat. There are photographs too. Human beings eating, laughing, studying, running. Images of Earth's landscapes and scientific knowledge encoded for hypothetical discoverers. The records were never truly intended as practical communication devices. The odds of another civilization finding Voyager are extraordinarily tiny. Instead, the Golden Records function partly as statements, proof that humanity looked outward and chose to introduce itself peacefully, which feels unexpectedly moving. Faced with the infinite darkness between stars, humans sent music. Bach, Beethoven, Chuck Berry, traditional songs from around the world. A species uncertain of its future deciding that if something eventually discovered our spacecraft, it should know we made art. Perhaps that is one of the most hopeful things humans have ever done. And now Voyager drifts through interstellar space carrying those sounds forever, long after Earth changes beyond recognition. Long after modern nations disappear. Long after today's languages evolve into entirely different forms, the spacecraft will continue moving silently through the galaxy. One fascinating thing about Voyager's future is that it will not approach another star closely for tens of thousands of years. Voyager 1 is heading generally toward the constellation Ophiuchus. In about 40,000 years, it will pass relatively near another star. 40,000 years. Human civilization itself is younger than that. It becomes difficult to emotionally process timescales so vast. and perhaps that is part of why the Voyagers matter so much psychologically. They stretch the human imagination. They force us to think beyond ordinary lifetimes, beyond generations, beyond civilizations. The spacecraft also remind us how recent space exploration truly is. The first powered flight on Earth occurred in 1903. Only 66 years later, humans walked on the moon. And less than a century after inventing airplanes, humanity launched machines that eventually crossed into interstellar space. The acceleration of technological progress during the 20th century remains almost unbelievable when viewed historically. Yet the Voyagers also embody patience. They travel slowly by cosmic standards. Their mission unfolds across decades. Interstellar exploration requires endurance more than speed, and perhaps there is something calming about that realization. The universe does not rush. Stars evolve over billions of years. Galaxies rotate slowly through darkness. Interstellar clouds drift patiently between suns. Voyager fits naturally into that rhythm, quiet, persistent, unhurried. Even now, while you listen, Voyager 1 moves farther from Earth than any object humanity has ever created. The distance grows every second. And somewhere beyond the heliopause, beyond the hydrogen wall, beyond the sun's protective bubble, our tiny robotic travellers continue slipping deeper into the strange darkness between stars, carrying human voices with them into the galaxy forever. Out beyond the heliopause, beyond the sun's protective bubble, the galaxy becomes a harsher place, not visibly harsher. A human standing somehow in interstellar space would not see glowing danger signs floating in the darkness. The stars would still shine quietly. Space would still appear mostly empty. There would be no obvious indication that the environment had changed dramatically. But invisible particles would be racing through that darkness at nearly the speed of light. Cosmic radiation, one of the most powerful and dangerous forms of energy in the universe, and one of the main reasons the heliosphere matters so profoundly for life on Earth. When people hear the word radiation, they often imagine glowing green barrels from old cartoons or dramatic science fiction accidents involving unfortunate laboratory technicians. Real cosmic radiation is less theatrical, but far more fascinating. Cosmic rays are mostly high-energy particles, usually protons, sometimes atomic nuclei stripped of their electrons entirely. These particles travel across the galaxy at extraordinary speeds after being accelerated by violent cosmic events. Supernova explosions launch many of them. Others likely originate near black holes or neutron stars where magnetic fields become unimaginably intense. Some cosmic rays may have travelled for millions of years through interstellar space before reaching our solar system. Tiny bullets fired by the galaxy itself, and unlike ordinary sunlight, cosmic rays possess enough energy to punch through matter in dangerous ways. When they collide with living tissue, they can damage cells directly. DNA strands break apart, mutations occur, long-term exposure increases cancer risks significantly. Earth is constantly bombarded by cosmic radiation even now, but most of us never notice because we are protected by multiple overlapping shields. First comes Earth's atmosphere, then Earth's magnetic field, and farther outward still, the heliosphere. The wall around our solar system helps reduce the number of dangerous galactic particles reaching the inner planets. Without it, Earth would likely be a far more hostile place for life. One of the strangest things about cosmic radiation is that it becomes more dangerous precisely because space is mostly empty. On Earth, air and matter absorb radiation relatively efficiently. Our atmosphere acts like an enormous protective blanket. High-energy particles collide with atmospheric molecules long before reaching the surface. Those collisions create secondary particle showers spreading through the atmosphere. Some still reach the ground, but much of the original energy gets dispersed safely overhead. The heliosphere performs a similar role on a vastly larger scale. The sun's magnetic field and outward flowing solar wind deflect many incoming cosmic rays away from the inner solar system. Not all of them, certainly. Some still penetrate inward. But Voyager's measurements beyond the heliopause confirmed something scientists strongly suspected. Outside the heliosphere, cosmic radiation levels rise dramatically. The galaxy beyond our solar system is significantly more radioactive than the space surrounding Earth. That realization changes the emotional meaning of the heliosphere slightly. The sun is not merely a source of warmth and light, it is also functioning as a gigantic shield. Stars, it turns out, can protect as well as threaten. That duality feels very appropriate somehow. The same sun capable of unleashing solar storms powerful enough to disrupt satellites and electrical systems is also helping defend Earth from even harsher galactic conditions beyond. Nature rarely gives simple answers. The heliosphere accomplishes this shielding through magnetism and plasma interactions. Cosmic rays are charged particles, which means magnetic fields influence their motion. As galactic cosmic rays approach the heliosphere, many become deflected by the sun's magnetic environment. The solar wind itself contributes to this protective effect. Streams of charged particles flowing outward create turbulence and magnetic structures that make it harder for some cosmic rays to penetrate deeply into the solar system. Think of it almost like trying to swim upstream through a powerful river current, while the river itself twists unpredictably. Some particles make it through, others get scattered away. The stronger the solar activity, the stronger this shielding effect tends to become, which creates one of the more ironic features of space weather. During periods of intense solar activity, Earth faces greater risk from solar storms originating from our own star, but slightly less exposure to galactic cosmic rays from outside the heliosphere. The Sun becomes more dangerous locally while simultaneously improving protection against deeper cosmic threats. Space really enjoys complicated trade-offs. One especially fascinating detail is that astronauts become far more exposed to cosmic radiation once they leave Earth's magnetic field. On the International Space Station, astronauts already receive significantly higher radiation doses than people on Earth's surface. Earth's atmosphere no longer surrounds them fully, although the station still remains partially protected by Earth's magnetosphere. Future missions to Mars present much greater challenges. Travelling astronauts would spend months outside Earth's strongest protective shields, while still remaining inside the heliosphere itself. Even there, radiation exposure becomes a serious medical concern. Beyond the heliosphere entirely, conditions grow harsher still. This is one reason interstellar travel remains extraordinarily difficult in reality. Science fiction often portrays deep space voyages as technologically challenging, but fundamentally manageable. Real physics is less accommodating. Cosmic radiation damages both electronics and biology over long periods. Human beings evolved beneath thick atmospheric shielding on a magnetized planet deep inside a heliosphere. Outside those protections, the galaxy feels very different, and yet life on Earth exists partly because these protective layers developed successfully over billions of years. Earth's magnetic field deflects solar wind and charged particles. The atmosphere absorbs harmful radiation. The heliosphere reduces incoming cosmic ray intensity from interstellar space. Together, these systems create a relatively stable environment where biology can flourish. Sometimes astronomy makes Earth feel small, other times it makes Earth feel astonishingly fortunate. One particularly dramatic example of radiation's power appears on Mars. Long ago, Mars likely possessed a thicker atmosphere and flowing liquid water. But after losing much of its global magnetic field billions of years ago, the planet became increasingly vulnerable to solar wind stripping. Tiny charged particles flowing outward from the Sun gradually eroded the Martian atmosphere over immense stretches of time. A planet changed fundamentally by invisible particles. That idea still feels almost surreal. The solar wind sounds intangible because individual particles are microscopic. Yet over geological timescales, their effects become enormous. Cosmic radiation behaves similarly. Single particles rarely matter much. Endless bombardment over millions or billions of years changes worlds. Another fascinating thing about cosmic rays is how energetic some of them become. The most extreme cosmic rays detected possess energies millions of times greater than particles accelerated in humanity's largest particle colliders. Scientists still debate exactly how some of these particles reach such astonishing speeds. Supernova shockwaves likely explain many cosmic rays, but the most energetic examples remain mysterious. Some may originate from active galactic nuclei surrounding supermassive black holes. Others perhaps from exotic astrophysical events we still poorly understand. The universe continues manufacturing particles far beyond anything human technology can currently produce, and many of those particles drift toward us continuously through interstellar darkness. The heliosphere softens that bombardment, quietly, constantly, without most people ever realizing it exists. There is something oddly comforting about that hidden protection. Every human civilization in history developed inside the heliosphere. Every species alive on Earth evolved within this sheltered region around the Sun. The wall around our solar system is not merely a scientific curiosity. It helps shape the biological conditions allowing complex life to survive here at all. One interesting consequence of cosmic radiation involves cloud formation hypotheses. Some researchers have proposed that cosmic ray intensity might influence Earth's climate slightly by affecting cloud nucleation processes in the atmosphere. The idea remains debated scientifically, but it highlights something important. The heliosphere may influence Earth in subtle ways we still do not fully understand, because the heliosphere changes over time. As the Sun moves through the galaxy, interstellar conditions shift. If the solar system enters denser interstellar regions in the distant future, the heliosphere could compress significantly. That compression might allow more galactic cosmic rays into the inner solar system. Earth's radiation environment could change, possibly even affecting atmospheric or biological systems over long timescales. Galactic neighborhoods matter. Our star does not drift through empty nothingness. It moves through a dynamic Milky Way filled with varying conditions, and the heliosphere acts as Earth's first great line of defense against those changing environments. Voyager's observations beyond the heliopause gave scientists direct measurements of just how much radiation levels increase outside the heliosphere. The rise in galactic cosmic rays was unmistakable. The spacecraft had entered a region where the Sun's protective influence weakened dramatically. There's something emotionally powerful about that realization. The darkness beyond the wall around our solar system is not simply empty, it is active, energetic, filled with particles carrying unimaginable energies across the galaxy. And yet here on Earth, beneath layers of shielding, life continues peacefully. Rain falls, forests grow, people sleep beneath blankets while tiny particles from exploded stars race invisibly across the cosmos overhead. Most of them never reaching the surface because our planet exists inside nested protective systems stretching all the way out to the heliosphere itself. One especially beautiful aspect of this story is that the Sun unintentionally protects life simply by being a star. The solar wind emerges naturally from stellar physics. The heliosphere forms automatically through interactions between that wind and interstellar space. No design, no purpose, no intention. Yet one consequence is safety. The same physical processes producing sunlight and auroras also help shield Earth from cosmic radiation. Sometimes the universe produces conditions favourable to life not through miracles but through ordinary physics operating across enormous scales. That realization feels strangely grounding. The cosmos is not carefully arranged around humanity, but neither is it entirely hostile. We emerged within environments shaped by stars, magnetism, atmospheres, and planetary dynamics. And for billions of years, the heliosphere has been part of that protective architecture. The farther scientists study cosmic radiation, the more they appreciate how difficult long-term interstellar travel truly becomes. Future spacecraft may require enormous shielding systems, Underground habitats on Mars may become necessary for reducing radiation exposure. Even advanced propulsion systems would not eliminate the biological challenges posed by years or decades beyond the heliosphere. The galaxy outside our solar system is beautiful, but it is not gentle. And perhaps that makes Earth feel more precious rather than less. Astronomy sometimes frightens people because cosmic scales are so enormous and human beings appear so small by comparison. Yet another perspective exists. Despite the harshness of interstellar space, life found shelter here, inside a planetary atmosphere, inside a magnetic field, inside a heliosphere, nested protection surrounding one tiny world, orbiting one ordinary star in the Milky Way. The farther Voyager travelled beyond the heliopause, the clearer this became. Humanity had crossed the boundary protecting us from much of the galaxy's radiation. Outside the wall, cosmic rays intensified. Interstellar space revealed itself as a harsher environment than the one surrounding Earth, and yet even there Voyager continued onward patiently, tiny, persistent, a machine built by creatures who evolved safely inside the sun's invisible magnetic bubble, still drifting farther into the strange radioactive darkness between stars. For a very long time, scientists imagined the heliosphere as something fairly simple, a bubble, neat, rounded, almost symmetrical. After all, the sun sits near the centre of the solar system, continuously blowing the solar wind outward in every direction. Intuitively, that should create a mostly spherical structure surrounding the planets, rather like an expanding balloon in space. And honestly, that idea feels emotionally satisfying too. Human beings like round things in astronomy. Planets are round, stars are round, soap bubbles are round. Even children drawing the solar system tend to instinctively sketch circles and gentle curves because symmetry feels comforting. But nature once again refused to cooperate quite so politely. The farther scientists studied the heliosphere, the stranger its shape became. And now, after decades of spacecraft measurements, computer simulations and observations of interstellar particles, researchers believe the bubble surrounding our solar system may not be round at all. In fact, nobody fully agrees on what shape it actually is, which is wonderfully typical of the universe. Just when humans begin feeling confident about understanding something enormous, reality quietly rearranges itself into a far more complicated form. At first, the spherical model seemed reasonable because the solar wind expands outward from the sun continuously. Early astronomers assumed this outward pressure would create a smooth bubble in all directions. But there was a hidden problem with that assumption. The solar system is moving, very fast. The sun orbits the centre of the Milky Way at roughly 828,000 kilometers per hour. Everything gravitationally bound to the sun moves with it. Earth, Mars, Jupiter, comets, Voyager, all travelling together through interstellar space. And once scientists accounted for that motion, the shape of the heliosphere immediately became more complicated. Imagine sticking your hand out of a car window while driving. Air pressure builds against the front of your hand while turbulence trails behind it. The faster the motion, the stronger the distortion. Something similar happens to the heliosphere. As the solar system moves through the interstellar medium, particles and magnetic fields press against the heliosphere unevenly. The front side facing the direction of motion becomes compressed. The trailing side stretches outward. This led many scientists to picture the heliosphere as comet-shaped. Rounded at the front, trailing a long tail behind. That model dominated scientific thinking for years, and honestly it makes intuitive sense. Comets themselves behave similarly when interacting with the solar wind. Their tails stream away dramatically through space. So perhaps the heliosphere should develop a long tail while moving through the galaxy too. Except then the data became annoying. Not wrong exactly, just inconveniently complicated. Voyager observations, energetic particle measurements, and data from missions like IBEX, the Interstellar Boundary Explorer, began suggesting the heliosphere might not possess an enormous trailing tail after all. Instead, the Sun's magnetic field appeared to influence the structure much more strongly than expected. And that changed everything. Magnetic fields in space behave with extraordinary power over plasma. Since the solar wind consists of charged particles, magnetism shapes its motion continuously. The Sun's magnetic field twists outward in spirals because the Sun rotates while emitting the solar wind. This creates enormous magnetic structures stretching across the heliosphere. Scientists eventually realized these magnetic effects might squeeze and shape the heliosphere into something entirely different from the classic comet model. One particularly surprising proposal suggested the heliosphere may resemble a croissant. Yes, a croissant. Few moments in astrophysics are more delightful than discovering the protective bubble surrounding our solar system may be shaped vaguely like breakfast pastry. The croissant model emerged because strong solar magnetic fields could funnel solar wind plasma into two jet-like lobes extending behind the solar system, rather than one enormous tail. Instead of stretching smoothly backward like a comet, the heliosphere might split into two broad curved structures. The universe occasionally sounds like it was designed by someone becoming increasingly whimsical halfway through creation. Still, despite the amusing comparison, the physics behind the idea is serious. Magnetic forces dominate plasma behavior over huge distances. The Sun's magnetic field may effectively pinch and redirect flows within the heliosphere, altering its overall structure dramatically. And because humanity remains trapped inside the heliosphere while studying it, determining the exact shape becomes incredibly difficult. It's rather like trying to map the shape of a forest while standing somewhere deep inside it with only a flashlight and partial information. We cannot step outside the heliosphere and photograph it directly, at least not yet. So scientists must infer its structure indirectly through measurements of particles, magnetic fields, and energetic neutral atoms. That last category deserves explanation because it led to one of the most important discoveries about the heliosphere. The IBEX mission launched in 2008 specifically to study interactions near the edge of the heliosphere. Unlike Voyager, IBEX didn't physically travel toward the boundary. Instead, it observed energetic neutral atoms arriving from the outer heliosphere. These particles form when charged solar wind particles interact with neutral atoms from interstellar space. Because neutral atoms are not affected strongly by magnetic fields, they travel relatively straight paths. By detecting them, IBEX could essentially create a rough map of distant heliospheric regions, and the map revealed something nobody expected: a giant ribbon, an enormous narrow band of energetic particles stretching across the sky. The IBEX ribbon. Scientists had not predicted it beforehand, which by now probably surprised absolutely nobody in astrophysics. The ribbon likely forms because interstellar magnetic fields interact with particles near the heliosphere's boundary in very specific ways. But researchers still debate exactly how the structure works. What matters here is that the ribbon revealed the heliosphere's shape, a magnetic environment are far more complex than earlier simple models suggested. The galaxy itself influences the shape of our solar system's protective bubble. Interstellar magnetic fields press against the heliosphere unevenly, and magnetic pressure matters tremendously in plasma physics, sometimes more than particle pressure alone. One fascinating consequence of all this is that the heliosphere likely changes shape over time. As the Sun moves through different interstellar environments, external pressures shift. Solar activity changes too. During periods of high solar activity, the solar wind strengthens, and the heliosphere may expand somewhat. During quieter periods, it contracts. The solar system's bubble flexes continuously, not rapidly enough for humans to notice directly, certainly. You will not wake tomorrow morning to discover the heliosphere developed an unfortunate dent overnight. But over years, decades, and centuries its structure evolves. That dynamism makes the heliosphere feel strangely alive again, despite being governed entirely by physical processes, breathing, flexing, responding to the galaxy around it. And perhaps the strangest realization of all is this: the shape of the heliosphere affects conditions throughout the solar system. Cosmic radiation shielding changes depending on heliospheric structure. Particle flows shift. Magnetic turbulence evolves. The geometry of our star's invisible bubble influences life deep inside it, including life on Earth. One especially important factor shaping the heliosphere is the local interstellar magnetic field. Magnetic fields thread through the Milky Way across enormous distances. Though weak compared to everyday magnets on Earth, these fields influence plasma motion profoundly because space is so thinly populated with matter. The heliosphere moves through those galactic magnetic structures continuously, and the interactions become incredibly complicated mathematically. Computer simulations attempting to model the heliosphere require enormous computational power because researchers must account for plasma dynamics, magnetic fields, solar cycles, particle populations, and interstellar conditions simultaneously. Nature is under no obligation to remain computationally convenient. Another reason the heliosphere may lack symmetry involves the Sun itself. The solar wind does not emerge uniformly everywhere. Different regions of the Sun produce different wind speeds and magnetic structures. Coronal holes generate faster solar wind streams. Solar maximum periods create more chaotic outflows. The Sun is turbulent and uneven. Therefore, the heliosphere becomes turbulent and uneven too. Everything connects, and this connection extends astonishingly far outward. The heliosphere stretches far beyond Pluto, far beyond the Kuiper Belt, far beyond regions most people associate emotionally with the solar system at all. The planets themselves occupy only a tiny fraction of the Sun's larger magnetic territory. If the heliosphere were reduced proportionally to the size of North America, the planetary orbits would occupy only a tiny central region, while the outer heliosphere stretched far into surrounding oceans. Most of our solar system is invisible structure rather than planets. That thought changes the emotional map of space slightly. Children often learn the solar system as a collection of worlds orbiting the Sun neatly in darkness. But in reality, we exist inside a giant moving magnetic environment interacting constantly with the galaxy itself. The planets are passengers inside something much larger, and because the heliosphere's shape remains uncertain, humanity still does not fully understand the structure surrounding us. That uncertainty feels important. Modern civilization sometimes gives the impression that science has already explained nearly everything significant. Yet the exact shape of the Sun's magnetic bubble remains actively debated. There is still mystery surrounding the environment enclosing our entire planetary system. That should be comforting in a way. The universe has not become smaller simply because humans learned more about it. If anything, it became stranger. One particularly eerie aspect of heliospheric structure involves the possibility of instabilities and distortions forming along the boundary. Magnetic reconnection events may occur where interstellar and solar magnetic fields interact. Plasma turbulence may ripple across huge regions. The heliopause itself may wrinkle and fluctuate dynamically under changing pressures. The edge of the solar system behaves less like a smooth shell and more like weather. Again, space repeatedly turns into weather if you zoom out far enough. The solar system is surrounded by cosmic climate systems shaped by plasma and magnetism rather than air and water, and all of this complexity remains invisible to ordinary human senses. There are no glowing outlines in the night sky revealing the heliosphere's shape. You cannot step outside and observe its curves overhead. Yet the structure surrounds us constantly. Right now, Earth moves through this enormous magnetic bubble, while rotating beneath sleeping cities and drifting clouds. Most people will never think about the heliosphere at all during their lives, and honestly, that is understandable. daily existence already requires remembering passwords, paying bills, and occasionally pretending to understand furniture assembly instructions. Still, once you learn about the heliosphere, it becomes difficult not to imagine it. A giant invisible structure surrounding the solar system, distorted by galactic magnetic fields, shaped by the sun's endless outward breath. Possibly resembling a comet, possibly a croissant, possibly something stranger still. Long before human beings understood magnetism scientifically, people noticed that certain strange stones could pull iron toward themselves. Ancient sailors later learned to use magnetized needles for navigation. Compasses pointed north reliably, even when clouds hid the stars. Invisible forces stretched across Earth itself, guiding travelers through darkness and storms. At the time, nobody could have imagined that magnetism also shapes the structure of the entire solar system. Not metaphorically, literally. The sun is surrounded by gigantic magnetic fields extending billions of kilometers into space. Those fields twist through the heliosphere, shape the solar wind, influence planetary environments, and help form the invisible wall surrounding everything we know. Without magnetism, the heliosphere as we understand it would not exist at all. And the farther scientists studied these magnetic fields, the stranger they became, because magnetism in space behaves nothing like the small refrigerator magnets or compasses humans encounter in daily life. In the vacuum between planets, magnetic fields dominate the motion of plasma across distances so vast they almost stop feeling physically real. They become architecture, invisible structure shaping the solar system itself. To understand these enormous magnetic fields, we need to begin inside the sun. The sun is not solid. That detail matters enormously. If the sun were a rigid body like Earth, its magnetic behavior would be far simpler. But the sun consists almost entirely of plasma, the electrically charged state of matter formed when atoms become so energetic that electrons break free. And plasma moves. It churns continuously inside the sun. Huge convection currents carry hot material upward, while cooler plasma sinks downward again. Meanwhile, different parts of the sun rotate at different speeds. The equator rotates faster than the poles. That uneven motion twists magnetic fields relentlessly. Scientists call this process the solar dynamo, and it generates magnetic structures on scales almost impossible to visualize comfortably. At first glance, the sun appears relatively calm from Earth, a bright disk hanging peacefully in the daytime sky. But beneath that appearance lies astonishing complexity. Magnetic fields rise through the sun's surface constantly. They twist into giant loops. They knot together. They reconnect violently. Sunspots form where magnetic activity temporarily cools portions of the visible surface. Solar flares erupt when magnetic energy releases suddenly into surrounding plasma. Coronal mass ejections blast billions of tons of charged particles into space. The sun is less like a peaceful glowing sphere and more like a gigantic magnetic engine continuously rearranging itself. And those magnetic fields do not remain trapped near the sun. The solar wind carries them outward through the solar system continuously. As charged particles stream away from the sun, magnetic field lines stretch outward with them. Because the sun rotates while releasing the solar wind, the magnetic field twists into a giant spiral structure called the Parker spiral. Imagine a spinning lawn sprinkler spraying water outward continuously. The streams curve because the sprinkler rotates. The sun does something similar with plasma and magnetism, except instead of watering grass, it shapes the magnetic environment of the entire solar system. That spiral magnetic field extends billions of kilometers outward. Earth moves through it constantly. So does every other planet. And because the solar wind varies over time, the magnetic environment surrounding the planets changes too. Space is not static. The heliosphere itself is magnetic weather. One especially fascinating thing about solar magnetic fields is that they reverse completely approximately every 11 years. North becomes south, south becomes north. The entire magnetic orientation of the Sun flips. This happens during periods of intense solar activity called solar maximum. Sunspots multiply, solar flares become more frequent, coronal mass ejections erupt more violently. The Sun's magnetic field grows tangled and unstable before eventually reorganizing itself into the opposite orientation. Then the cycle begins again. There is something oddly comforting about that rhythm. Even stars have cycles. The Sun itself experiences periods of relative calm and turbulence, like enormous cosmic seasons unfolding across decades. Earth exists inside those changing magnetic conditions continuously. Sometimes the effects become visible. Auroras are among the most beautiful examples. When charged particles from the solar wind interact with Earth's magnetic field, many become guided toward the poles along magnetic field lines. There they collide with atmospheric gases, producing shimmering curtains of light across the sky. Green, purple, red. Silent glowing waves moving above frozen landscapes and sleeping cities. Auroras are essentially visible magnetism, the sky briefly revealing the invisible structures surrounding Earth. And those structures connect outward through the heliosphere all the way back to the Sun itself. Earth possesses its own magnetic field generated by molten iron moving inside the planet's outer core. This field forms the magnetosphere, a protective bubble deflecting much of the solar wind around Earth. Without it, the atmosphere would face far greater erosion from solar particles over long timescales. Mars provides a sobering comparison once again. Unlike Earth, Mars lost most of its global magnetic field billions of years ago. Without strong magnetic shielding, the solar wind gradually stripped away much of the Martian atmosphere. Magnetic fields help determine whether worlds remain habitable. That realization changed planetary science profoundly. For a long time, researchers focused mainly on distance from the Sun when considering planetary habitability. But now scientists understand magnetic protection matters enormously too. A planet may orbit in the habitable zone where liquid water could exist, yet still face devastating atmospheric loss without sufficient magnetic shielding. Invisible fields shaping planetary destiny. The heliosphere itself depends heavily on magnetism as well. The boundary regions near the heliopause are not shaped purely by particle pressure. Interstellar magnetic fields press against the heliosphere continuously, distorting its structure. This is one reason scientists still debate the heliosphere's true shape. Magnetism complicates everything. In plasma physics, magnetic fields can dominate particle motion entirely. Charged particles spiral around field lines rather than travelling freely. As a result, the heliosphere behaves less like a simple expanding gas bubble, and more like an enormous magnetic organism responding dynamically to galactic forces. Again, not alive biologically, but certainly active, responsive, changing. One particularly strange discovery involved the Ibex ribbon, detected by the Interstellar Boundary Explorer mission. Scientists had expected energetic particles near the heliosphere's edge to distribute relatively smoothly. Instead, Ibex discovered a giant ribbon-like structure of energetic neutral atoms stretching across the sky. The ribbon appears closely linked to interstellar magnetic field orientation outside the heliosphere. Essentially, the galaxy's magnetic structure shapes the particle environment around our solar system directly. That realization feels profound somehow. The Milky Way itself influences the invisible magnetic cocoon surrounding Earth. We are connected to galactic-scale structures whether we notice them or not. Voyager's journey beyond the heliopause provided even more fascinating magnetic observations. Scientists expected a dramatic directional shift in magnetic fields once Voyager entered interstellar space, but the transition proved surprisingly subtle. The interstellar magnetic field outside the heliosphere aligned more closely with the heliospheric field than anticipated. Researchers still debate exactly why. Some suspect the local galactic magnetic environment naturally orients similarly near the boundary. Others think complex plasma interactions smooth the transition region more than models predicted. Either way, the discovery reminded scientists that magnetic structures across space remain deeply interconnected. Nothing exists entirely in isolation. Even the Sun's enormous magnetic bubble blends gradually into the wider magnetic fabric of the galaxy. Another extraordinary aspect of cosmic magnetism is its scale. On Earth, magnetic fields feel local and manageable. Compasses point north, magnets stick to surfaces. Hospital MRI machines produce powerful magnetic fields inside carefully controlled rooms. In space, magnetic fields stretch across light years. Entire galaxies possess magnetic structures. Interstellar gas clouds respond to them. Star formation itself may depend partly on magnetic interactions controlling how collapsing gas behaves. The universe is threaded with invisible magnetic architecture, and humanity evolved inside one tiny protected corner of it. One especially interesting consequence of magnetic fields involves cosmic radiation. As we explored earlier, the heliosphere helps shield the inner solar system from many galactic cosmic rays. Magnetism plays a central role in this protection. Charged particles from interstellar space interact with the heliosphere's magnetic environment as they approach. Some become deflected away, others scatter through turbulent magnetic regions. Without those magnetic interactions, far more dangerous radiation would penetrate deep into the solar system. The Sun's magnetic field helps create a giant protective barrier surrounding Earth, which means magnetism influences life itself more profoundly than most people realize. Every tree, every ocean, every sleeping city, all existing inside overlapping magnetic shields extending from Earth's core out through the heliosphere. There's something strangely comforting about that invisible protection. Most people move through life entirely unaware of magnetic structures surrounding them constantly, and perhaps that is understandable. Human senses evolved for survival on Earth's surface, not for perceiving electromagnetic geometry spanning billions of kilometers. We see light, we feel heat. We hear vibrations in air, but magnetism remains hidden from direct perception, and yet it shapes enormous portions of reality. One of the strangest things about magnetic fields is that they store energy. Twisted magnetic field lines within the Sun can suddenly reconnect explosively, releasing tremendous amounts of energy during solar flares and coronal mass ejections. These events launch charged particles outward across the solar system. When strong enough, they can disrupt satellites, communication systems, and power grids on Earth. The Sun's magnetic mood swings occasionally ripple all the way down to human civilization. Again, the solar system feels less isolated and mechanical once you understand this. It becomes alive with interactions, fields, particles, flows, invisible structures constantly shifting through darkness, and Earth rides inside all of it continuously. Even now, while you listen, magnetic field lines from the Sun stretch across the heliosphere around the solar system. Solar wind plasma streams outward, carrying those fields toward interstellar space. Beyond the heliopause, galactic magnetic fields press inward from the wider Milky Way. The boundaries between these environments ripple and shift across enormous distances. Meanwhile, deep inside the heliosphere, life continues peacefully on one small planet. Children sleep, rain falls, cities glow softly at night, and surrounding everything is a giant invisible magnetic architecture generated by an ordinary yellow star. Perhaps one reason astronomy feels emotionally powerful is that it reveals how connected things truly are. The Sun influences Earth not only through light and gravity, but through magnetism stretching billions of kilometers into space. The galaxy influences the heliosphere through interstellar magnetic pressure. The universe turns out to be woven together by structures we cannot even see directly. And still, despite all we have learned, enormous mysteries remain. Scientists still do not fully understand magnetic reconnection processes. Solar cycle behavior remains partly unpredictable. The exact structure of interstellar magnetic fields near the heliosphere continues to be debated. There are invisible forces surrounding us that humanity only barely understands. That should not feel discouraging. If anything, it should feel exciting. The universe still contains mysteries large enough to surround the entire solar system. Somewhere out there in the Milky Way tonight, other stars are moving through the galaxy wrapped inside invisible bubbles of their own. That idea feels almost unavoidable once you understand the heliosphere. If our sun creates a giant magnetic boundary by releasing the solar wind into interstellar space, then surely other stars must be doing something similar. After all, the sun is not especially unusual as stars go. It is fairly ordinary, medium-sized, stable, calm compared to many of the violent monsters scattered throughout the galaxy. And if an ordinary star like the Sun can inflate a magnetic cocoon large enough to surround an entire planetary system, what might happen around stranger stars? The answer, according to modern astronomy, is both comforting and fascinating. Yes, other stars almost certainly have walls too. Scientists call them astrospheres. The heliosphere is simply the astrosphere surrounding our own Sun. Every star producing a stellar wind and magnetic field likely carves out its own protective cavity in interstellar space. Giant invisible bubbles drifting through the Milky Way, each shaped by the interaction between stellar winds and the galaxy beyond. Which means the Milky Way may be filled with overlapping stellar territories moving through darkness together. That changes the emotional image of the galaxy quite a bit. Instead of isolated stars scattered through empty space, the Milky Way becomes a crowded ocean of invisible magnetic structures constantly colliding, flexing, and interacting. Some tiny, some enormous, some violent beyond imagination. And around many of them, perhaps planets orbit quietly inside those protective bubbles just as Earth orbits safely inside ours. The first clues about astrospheres came naturally from understanding the heliosphere itself. Once astronomers realized the Sun's solar wind creates a magnetic cavity in interstellar space, the logic extended immediately to other stars. Many stars possess stellar winds. Many stars produce magnetic fields. Therefore, many stars should shape their surrounding environments in similar ways. The details, however, vary enormously depending on the kind of star involved. And this is where things become wonderfully strange. The Sun feels enormous to us because it dominates our lives completely. But astronomically speaking, the Sun is remarkably moderate. There are stars far larger, far hotter, far more magnetic, far more violent. Some stars release stellar winds vastly stronger than our Sun's. Others produce weaker winds. Some rotate so rapidly that their magnetic fields become twisted into astonishingly powerful structures, stretching across huge distances. The resulting astrospheres likely differ dramatically throughout the galaxy. Around red dwarf stars, for example, conditions may become especially intense. Red dwarfs are the most common stars in the Milky Way. Smaller and cooler than the Sun, they can remain stable for trillions of years. Yet many red dwarfs are magnetically active to an extraordinary degree. They produce powerful stellar flares frequently. Some erupt with such intensity that nearby planets could experience enormous radiation exposure. If those stars possess astrospheres, the structures may behave very differently from our heliosphere. More compressed perhaps, more turbulent, more unstable. Planets orbiting red dwarfs often lie much closer to their stars than Earth lies to the Sun because the stars themselves are dimmer. That means those planets sit deep inside regions of intense magnetic activity. Scientists now wonder whether stellar magnetism and astrospheric shielding may play major roles in determining planetary habitability throughout the galaxy. Again and again, magnetism returns as one of the hidden architects of life. Massive stars create even stranger environments. Some enormous blue stars produce stellar winds millions of times stronger than the sun's solar wind. Their radiation output is staggering. Their lifespans are relatively short because they burn through nuclear fuel rapidly. Around such stars, astrospheres may become gigantic. Immense cavities blasted into surrounding interstellar gas by violent stellar winds. Astronomers actually observe some of these structures directly. Bow shocks form where massive stars plough through interstellar space, compressing gas ahead of them like ships moving through water. Infrared telescopes reveal glowing arcs surrounding certain stars, evidence of interactions between stellar winds and the interstellar medium. The galaxy contains stellar weather systems on scales difficult to emotionally process. One especially dramatic example involves runaway stars. Sometimes stars are ejected from their birth regions at high speed due to gravitational interactions or nearby supernova explosions. These stars race through the galaxy rapidly, and their astrospheres become distorted dramatically by the interstellar medium pressing against them. Some produce enormous glowing bow waves visible across light years. The star essentially carries its own moving bubble through the galaxy, like a ship generating waves across a dark ocean. Our Sun likely does something similar on a smaller scale. The hydrogen wall surrounding the heliosphere may be part of that same broader phenomenon, and perhaps somewhere around another star another civilization has looked outward and discovered its own invisible boundary too. That possibility feels strangely intimate. Different worlds, different suns, different skies, yet the same basic cosmic structures emerging again and again. Stellar winds, magnetic bubbles, protective walls against the galaxy beyond. One fascinating thing about astrospheres is that they may influence planetary evolution profoundly. A strong astrosphere could shield planetary systems from cosmic radiation more effectively. A weak one might expose planets to harsher interstellar environments. The size and strength of a star's astrosphere likely depends on many factors: stellar age, magnetic activity, rotation speed, interstellar conditions, the density of surrounding gas. Everything interacts. Young stars often possess stronger magnetic activity and more intense stellar winds. Their astrospheres may differ enormously from those surrounding older, calmer stars. Our Sun itself was likely far more violent billions of years ago when Earth was young. The early heliosphere may have behaved very differently from the one protecting us today. That realization matters because life evolved inside changing stellar conditions. The Sun was not always as calm as it appears now, and perhaps around countless other stars, astrospheres continue evolving while planets adapt beneath them. Astronomers have already detected indirect evidence for astrospheres around several nearby stars. One method involves studying hydrogen absorption patterns, similar to those used to detect our own hydrogen wall. Heated hydrogen surrounding other astrospheres leaves signatures in ultraviolet light, passing through those regions. By analysing those signatures, scientists can infer the presence of stellar wind bubbles around distant stars. Even from many light-years away, the walls around other stellar systems reveal themselves subtly. The galaxy leaves fingerprints everywhere if you know how to look. One particularly interesting case involves the star Alpha Centauri, the nearest stellar system to our own. Researchers suspect Alpha Centauri likely possesses its own astrosphere, shaped by the combined influence of its stars and their winds interacting with interstellar space. That means the nearest neighbouring stars may travel through the galaxy, wrapped inside invisible magnetic bubbles much like ours, and between those bubbles stretches true interstellar space, dark, cold, enormous, yet threaded with magnetic fields and drifting particles connecting everything together. Another fascinating implication involves exoplanets. Thousands of planets have now been discovered orbiting distant stars. Some may lie in habitable zones where liquid water could exist, but habitability may depend on far more than temperature alone. Astrospheric shielding could become crucial. A planet orbiting inside a strong protective astrosphere might experience relatively stable radiation conditions. Another orbiting inside a weak or unstable astrosphere could face intense cosmic radiation and atmospheric erosion. The invisible wall around a star may help determine whether life survives on worlds orbiting deep inside it. That idea feels profound. Entire ecosystems potentially depending on magnetic structures spanning billions of kilometers. And because stars vary so dramatically, the diversity of astrospheres across the galaxy is probably astonishing. Some may stretch huge distances outward, others may remain compressed and chaotic. Some stars travelling through dense interstellar clouds may possess distorted astrospheres squeezed tightly inward. Others moving through thinner regions may enjoy vast expansive magnetic territories. The galaxy itself shapes these structures continuously. One especially eerie possibility involves stars moving through dangerous regions of the Milky Way. Dense molecular clouds, supernova remnants, and regions of intense radiation could all affect astrospheric behaviour. A star entering a denser interstellar cloud might experience compression of its astrosphere, allowing more cosmic radiation to penetrate inward toward its planets. In other words, galactic weather could influence planetary environments across enormous timescales. Our solar system may have experienced such changes in the distant past, and countless other planetary systems almost certainly do as well. There is something strangely comforting about the universality of this process. The heliosphere once seemed unique simply because it surrounds us personally. But astronomy repeatedly teaches the same lesson. Nature loves patterns. Stars create winds, winds create bubbles, bubbles interact with the galaxy, again and again across the Milky Way. Perhaps that repetition helps explain why the universe feels comprehensible at all. The same physical laws operate everywhere. Magnetism behaves similarly around distant stars. Plasma flows follow familiar principles. Gravity shapes systems consistently. The cosmos is unimaginably vast, yet governed by recurring structures and interactions. Even so, every astrosphere remains unique because every star lives a different story. Some stars exist alone. Others belong to binary or triple systems where interacting stellar winds create much more complicated environments. Some stars rotate rapidly enough to amplify magnetic activity tremendously. Others age into quieter, calmer phases. The galaxy contains endless variations on the same fundamental themes. One remarkable thing about our own heliosphere is that humanity discovered it at all. The structure is invisible directly. We live inside it. And yet through careful observation, mathematics, spacecraft exploration, and astonishing patience, humans learned that the solar system possesses a giant magnetic boundary. Then we realized other stars likely possess them too. There is something deeply human about that progression. First understanding home, then understanding that home is not unique, and perhaps somewhere else in the Milky Way, another civilization sits beneath another star asking similar questions. What surrounds us? Where does our star's influence end? What lies beyond the wall? The answers may differ in detail. Different stars produce different astrospheres, but the larger truth appears universal. Stars do not exist in isolation. They shape space around themselves continuously, and planets, including Earth, live deep inside those invisible stellar territories. The farther astronomy advances, the more alive the galaxy begins to feel. Not alive biologically, perhaps, though the universe may contain life elsewhere too, but alive with motion, interaction, flow, invisible magnetic weather surrounding stars across the Milky Way. And among those countless stellar bubbles drifting through darkness is one small heliosphere surrounding an ordinary yellow star where human beings learned for the first time that they had been living inside a cosmic wall all along. Far beyond the planets, beyond the Kuiper belt, beyond even the heliopause itself, the solar system continues. That fact surprises many people the first time they hear it. After spending so much time travelling outward through the heliosphere, crossing the termination shock, drifting through the heliosheath, and finally reaching the boundary where the sun's magnetic influence gives way to interstellar space, it feels natural to assume we have reached the true edge of the solar system. But we have not even close. The heliopause marks the end of the sun's magnetic bubble. The Oort cloud marks something different entirely. It is the outermost gravitational frontier of the solar system, a vast shell of icy objects surrounding the sun at distances so enormous they barely feel real anymore. And somewhere out there, in the freezing darkness near the edge of the Oort cloud, the solar system slowly dissolves into the galaxy itself. The transition is not dramatic. No giant sign floats in space announcing you are now leaving the sun's territory forever. There is no sudden wall, no final border crossing. The sun's gravitational influence simply grows weaker and weaker until eventually nearby stars and the Milky Way itself begin tugging on objects almost as strongly as the sun does. That is where the solar system truly begins blending into interstellar space, and the distances involved are staggering. The planets occupy only a tiny inner region compared to the Oort cloud. Neptune orbits roughly 30 astronomical units from the Sun. The heliopause lies around 120 astronomical units away in some directions, but the Oort cloud may extend from roughly 2,000 astronomical units all the way out to perhaps 100,000 astronomical units or more. At those distances, sunlight becomes almost meaningless. The sun itself shrinks into a brilliant star among countless others, and yet objects out there may still remain gravitationally bound to it. The scale becomes difficult to emotionally process. If Earth's orbit were reduced to the size of a coin, the outer Oort cloud would stretch for kilometres. Most of the solar system is not planets. Most of it is dark emptiness filled with tiny frozen remnants left over from the birth of the sun itself. The Oort cloud is believed to contain trillions of icy bodies, comets, frozen fragments, ancient leftovers from the formation of the planets more than 4 billion years ago. When the solar system was young, giant planets like Jupiter and Saturn gravitationally scattered enormous numbers of icy objects outward. Some escaped the solar system entirely, others became trapped in extremely distant elongated orbits, forming the vast spherical cloud surrounding the sun today. That means the Oort cloud is ancient beyond ordinary comprehension. Many objects out there have likely remained nearly unchanged since before Earth even possessed oceans, before life existed, before the moon fully settled into its orbit. Tiny frozen time capsules drifting in darkness at the edge of the sun's gravitational reach. And despite its enormous size, the Oort cloud remains almost entirely hypothetical in one important sense. No spacecraft has ever reached it. No telescope has directly observed most of it. Astronomers infer its existence mainly because of long-period comets. Some comets enter the inner solar system from extremely distant random directions. Their orbits suggest they originated from a giant spherical reservoir far beyond the planets. That reservoir is the Oort cloud. One fascinating thing about the Oort cloud is how loosely its objects are bound to the sun. Closer planets orbit securely. Earth never worries about drifting away accidentally because the sun's gravity dominates strongly here. Out near the edge of the Oort cloud, however, the sun's grip becomes fragile. Passing stars can disturb objects there. So can giant molecular clouds drifting through the galaxy. Even the tidal gravitational forces of the Milky Way itself influence the outer Oort cloud. The solar system's edge is not stable and isolated. It interacts continuously with the galaxy beyond. And sometimes those interactions send comets inward toward the sun. A nearby passing star may slightly disturb an icy body in the Oort cloud. Over immense periods of time, that tiny disturbance changes the object's orbit enough to send it falling inward across the solar system. Eventually, after perhaps millions of years drifting through darkness, the comet reaches the inner solar system where sunlight begins vaporizing its ice, and creating the glowing tails humans see from Earth. Some of the most spectacular comets in history likely began their journeys this way. Visitors from the farthest edges of the solar system, perhaps from regions where sunlight is barely distinguishable from starlight. There is something strangely emotional about that idea. A comet appearing over Earth's skies may have spent billions of years frozen in darkness near the edge of the Oort cloud before gravity nudged it inward toward the sun. Human civilizations rise and fall in the time it takes such objects to complete a fraction of their enormous orbits. The farther outward you travel toward the Oort cloud, the less the solar system resembles the tidy planetary diagrams taught in schools. There are no orderly lines, no neat arrangement of worlds, only scattered icy objects separated by immense emptiness. In fact, even within the Oort cloud itself, distances between objects are probably enormous. If you stood on one hypothetical comet there, neighbouring objects might remain incredibly far away. The cloud is vast but sparse. Space remains overwhelmingly empty almost everywhere. One especially eerie aspect of the outer Oort cloud is the darkness. Near Earth, sunlight fills the sky. Even nighttime still carries traces of scattered solar illumination. The moon glows brightly. Planets shine clearly. Near the outer Oort cloud, sunlight becomes incredibly weak. The sun would appear merely as a brilliant star among many others. Bright enough to cast faint shadows perhaps, but no longer emotionally recognizable as the great blazing center of human life. That transition feels psychologically important somehow. Deep inside the solar system, the sun dominates existence completely. At the edge of the Oort cloud, the sun joins the galaxy. It becomes one star among countless stars, and beyond that region lies true interstellar space stretching between stellar systems. One fascinating question scientists debate involves where the solar system actually ends. Is it the heliopause, the edge of the heliosphere, or is it the edge of the Oort cloud where the sun's gravity finally loses dominance? The answer depends partly on what you mean by solar system. Magnetically, the heliopause represents the sun's boundary against interstellar space. Gravitationally, the Oort cloud extends vastly farther. Both definitions are valid. Which means humanity already crossed one edge of the solar system with Voyager, yet remains unimaginably far from crossing the other. That realization restores the scale of space immediately. Voyager 1, the most distant human-made object ever built, has travelled only a tiny fraction of the distance toward the outer Oort cloud. At its current speed, Voyager may require hundreds of years just to reach the inner regions of the Oort cloud, and tens of thousands of years to pass beyond it entirely. The solar system is larger than human intuition naturally allows. Another remarkable thing about the Oort cloud is how vulnerable it is to galactic events. Passing stars occasionally drift relatively near the sun over cosmic timescales. Most pass harmlessly, but their gravity can disturb the outer Oort cloud significantly. Some scientists think such disturbances may trigger increased comet activity in the inner solar system periodically. In other words, events occurring between stars could influence conditions near Earth millions of years later. Again and again, astronomy reveals how connected everything becomes across enormous distances. The Milky Way itself may shape the long-term history of comets impacting Earth. There's also a wonderfully unsettling possibility hidden within the Oort cloud discussion. If our solar system possesses such a distant cloud of icy bodies, other stars probably do too. Other stellar systems may be surrounded by their own vast reservoirs of frozen objects drifting near the edge of gravitational influence, and perhaps, occasionally, objects get exchanged. A comet loosely bound to one star might become captured by another over immense spans of time. Some researchers even suspect a few objects currently in the solar system may have originated around entirely different stars long ago. The galaxy exchanging material slowly across billions of years. That possibility makes the Milky Way feel strangely fluid rather than neatly separated into isolated systems. Stars drift, gravity interacts, objects wander between systems, everything moves. One particularly mysterious idea involves the hypothetical inner Oort cloud, sometimes called the Hills cloud. Scientists suspect a denser region of icy bodies may exist inside the outer Oort cloud itself. This inner cloud could contain enormous numbers of objects and serve as the true long-term reservoir replenishing the outer cloud over time. If correct, the structure of the solar system becomes even more layered and enormous than originally imagined. Again, the universe declines every opportunity to remain simple. The edge of the Oort cloud also represents one of the coldest environments associated with the solar system. Temperatures there hover only a few degrees above absolute zero. The objects drifting through those regions receive almost no solar warmth. And yet they continue orbiting patiently for billions of years, frozen relics from the birth of the Sun. One emotional aspect of the Oort cloud that often goes unnoticed is how isolated those objects truly are. A comet in the outer cloud may spend millions of years without experiencing any significant change at all. Darkness, cold, silence, only distant stars slowly shifting over unimaginable stretches of time, and yet eventually gravity may alter one orbit slightly. A passing star. Galactic tides. A tiny disturbance. Then after another immense span of time, the object begins falling inward toward the Sun, toward warmth, toward visibility, toward the inner solar system where humans might someday look upward and briefly admire the glowing tail of a traveller from the edge of darkness. There is something deeply beautiful about that journey. The Oort cloud also changes how we emotionally imagine the solar system itself. Instead of a compact family of planets, the solar system becomes a gigantic diffuse sphere stretching far into interstellar space. The planets are merely the bright crowded centre. Most of the solar system is dark frontier, and somewhere near the outer edge of that frontier, the distinction between our system and the galaxy slowly begins to disappear. That transition matters philosophically as much as scientifically. Human beings often crave clean borders and clear definitions. Nature rarely provides them. The edge of the Oort cloud is not a sharp ending, it is a fading influence, a gradual surrender of the Sun's dominance to the wider Milky Way. And perhaps that is fitting, because the Sun itself formed from galactic material long ago. The solar system emerged from interstellar gas and dust. One day, much of its material will likely return to the galaxy again. Nothing remains isolated forever. The farther outward you travel, the more the solar system begins blending back into the cosmic environment from which it came. And somewhere beyond the frozen darkness of the Oort cloud, beyond even the last faint traces of the Sun's gravitational authority, lies the true open ocean between stars. An ocean humanity has only just begun to touch. Late at night, when the world becomes quieter and the usual noise of daily life begins to fade a little, it becomes easier to think about where we actually are. Not your address, not your city, not even your planet, but where all of this exists in the larger sense. Because every human being who has ever lived has spent their entire life inside something invisible. A giant magnetic bubble surrounding the solar system, a moving boundary inflated by the Sun, a cosmic shelter drifting through the Milky Way. And for most of human history, nobody knew it was there. That fact feels strangely beautiful. Entire civilizations rose and fell beneath skies they thought they understood, while far beyond the planets the Sun's invisible influence stretched outward into darkness against the pressure of the galaxy itself. Kings lived and died inside the heliosphere. Dinosaurs lived inside it. The first fish crawling onto land lived inside it. Every war in human history happened deep within this enormous magnetic cocoon generated by an ordinary star. And only recently did humanity finally realize the wall existed at all. Astronomy often begins with objects, planets, stars, galaxies, things we can point toward. But the heliosphere is different. It is not a world, not a moon, not a planet. It is an environment, a region of influence, a protective territory surrounding everything we know. That changes the emotional feeling of the solar system slightly. The planets stop seeming isolated from one another. Instead, they become neighbours sharing the same giant shelter around the sun. Mercury exists inside it. Jupiter exists inside it. Tiny Pluto drifts within it too. Voyager crossed beyond it. And Earth, with all its oceans and forests and sleeping cities, rests safely near the centre of it. There's something comforting about that image. Human beings spend much of life building small protective spaces around themselves. Homes, blankets, walls, communities. We instinctively seek shelter, and in a strange cosmic sense, the heliosphere is another layer of shelter. Not perfect protection, certainly. The universe remains dangerous in many ways. Solar storms can still disrupt Earth. Asteroids still exist. Cosmic radiation still reaches us partly. But without the heliosphere, the solar system would be exposed more directly to the harshness between stars. The galaxy outside our bubble is beautiful. It is also violent. Supernova explosions scatter radiation across enormous distances. Cosmic rays race through interstellar space at nearly light speed. Magnetic turbulence ripples between stars, and around our solar system the sun pushes outward continuously against all of it, every second, every day, for billions of years. The sun's endless breath creates the wall around us, not intentionally. Stars do not care in the human sense. Yet one consequence of living beside a star is protection. That idea feels oddly emotional despite being pure physics. Sometimes the universe creates conditions favourable to life simply because physical laws unfold naturally in certain ways. No grand design required, just plasma, magnetism, gravity, time, and inside those conditions, life emerges. The farther humanity explored the heliosphere, the stranger and more intimate space became. At first, people imagined the solar system as a relatively tidy place, planets orbiting quietly in darkness. Then we discovered the solar wind, the heliosphere, the termination shock, the heliosheath, the heliopause, the hydrogen wall. Suddenly the solar system transformed from a collection of planets into a giant moving structure interacting constantly with the Milky Way. We are not floating motionless through empty space. We are travelling through a galactic ocean inside a magnetic bubble generated by our star. That realization changes your perspective slightly once it settles in. Even now, while you listen, Earth moves around the Sun at roughly 107,000 kilometers per hour. The Sun carries the entire solar system around the Milky Way at more than 800,000 kilometers per hour. And surrounding all of it is the heliosphere, pushing against interstellar space while drifting through the galaxy. Every human life unfolds aboard this moving vessel. Most of us never notice because human senses evolved for survival on Earth's surface, not for perceiving cosmic motion. And perhaps that is fortunate. Trying to emotionally process all these movements simultaneously before breakfast would probably exhaust most people immediately. Still, there is something calming about understanding them. The universe feels less static afterward, more alive, more interconnected. One of the most touching parts of this entire story remains Voyager. 2 tiny spacecraft launched in 1977 eventually reached the wall around our solar system and crossed beyond it. Humanity touched interstellar space for the first time not through conquest or colonization, but through curiosity. That feels important. The first objects humanity sent beyond the heliosphere were scientific instruments carrying music, photographs, greetings, and sounds from Earth. A species emerging from one small planet deciding to introduce itself gently to the galaxy. Even if nobody ever finds Voyager, the gesture matters emotionally, because it says something hopeful about humanity. Faced with infinite darkness, we sent art. We sent whale songs. We sent Bach. We sent greetings in dozens of languages. There is something wonderfully human about that decision. And now, Voyager drifts farther from Earth every second. Long after modern civilization changes beyond recognition, the spacecraft will continue moving through interstellar darkness, carrying tiny traces of humanity into the Milky Way, perhaps forever. The heliosphere also teaches something important about boundaries. Human beings love clear borders, maps, lines, definitions. We like knowing where things begin and end, but nature rarely works that way. The wall around our solar system is not a solid edge. It is a transition. The solar wind gradually weakens. Interstellar pressure gradually increases. Magnetic fields interact and blend. Even the edge of the Oort cloud fades slowly into the larger galaxy. Reality prefers gradients rather than sharp divisions, and perhaps life itself works similarly. Most meaningful changes happen gradually, quietly, without dramatic announcements. The night slowly becomes morning, childhood slowly becomes adulthood, civilizations evolve over centuries. Stars drift through the galaxy over millions of years. The heliosphere itself expands and contracts gently with the rhythm of solar cycles. Everything moves, everything changes, usually more softly than we notice day to day. Another strange comfort hidden inside this story is the realization that Earth is not exposed and isolated in the way many people instinctively imagine space. We often picture our planet as a tiny, fragile object floating helplessly in hostile emptiness. In some ways, that is true, but Earth also exists inside layers of protection. The atmosphere shields us, the magnetic field shields us, the heliosphere shields us, nested structures surrounding one small world. And beyond those layers lies the galaxy itself, cold, enormous, beautiful, dangerous. The stars beyond the heliopause are unimaginably distant. Even Voyager, travelling faster than any human-made object in history, will need tens of thousands of years to pass near another star meaningfully. That scale can sound frightening initially, yet strangely it can also feel peaceful. The universe is under no pressure to hurry. Galaxies rotate slowly. Stars evolve over billions of years. Interstellar clouds drift patiently through darkness. The cosmos moves at its own pace, and perhaps that is why astronomy helps many people relax. Not because space is small or simple, quite the opposite. Because the vastness gently loosens the grip of ordinary anxieties for a little while. Your worries still matter. Your life still matters deeply. But somewhere beyond Pluto, beyond the heliopause, beyond the hydrogen wall, the galaxy continues unfolding according to timescales so enormous they soften the edges of stress. The universe has existed for billions of years before us. It will continue long after us, and somehow that can feel comforting rather than depressing. We are temporary, but we are also part of something astonishingly large. One especially beautiful thing about the heliosphere is that it transforms the sun emotionally from merely a source of light into something closer to a guardian. Again, not intentionally. The sun is simply following physics, but the effect remains. Our star creates a giant magnetic refuge where planets can orbit relatively safely. Inside that refuge, oceans formed, atmospheres survived, life evolved. Eventually, one species began building telescopes and asking questions about the boundary surrounding them. And then, incredibly, that species learned enough physics to discover the wall itself. There's something poetic about that progression, without needing to become overly abstract about it. Tiny creatures on one small planet realizing they live inside the atmosphere of a star, because in many ways that is exactly what the heliosphere is. The sun's extended atmosphere surrounding the solar system. And tonight, somewhere above Earth's sleeping cities and quiet oceans, the solar wind continues flowing outward into darkness, beyond the planets, beyond Voyager, toward the heliopause, toward the hydrogen wall, toward the galaxy beyond. The heliosphere remains there whether anyone thinks about it or not. Invisible, enormous, protective, a moving bubble carrying every human story through the Milky Way. And perhaps that is the quiet meaning hidden inside all of this. We are small, but we are not alone in empty darkness. We travel together inside the sun's great invisible shelter, drifting through the galaxy beneath the light of one ordinary star.